Welcome, my fellow sleepless wanderer. You have found your way to the Sleepless Mathematician, where numbers are not just numbers, they are stories, mysteries, and sometimes the kind of bedtime tales that no sane person should tell before falling asleep. But that is the beauty of it. We take the kind of ideas that have kept mathematicians awake at night for centuries, and we whisper them to you slowly until they become soft enough to dream on. Tonight, we are going on a very strange journey. Not through space exactly, but through time, and not just in the way you are already doing, second by second while lying in bed. No, we are talking about time travel, the math of time travel, and maybe, just maybe, why it might actually be possible. Now, before you panic, I promise this will not involve building a DeLorean in your garage, or finding a spare black hole under your couch. You will not wake up in the year 3025, though if you do, please write me a postcard. What we are going to do is what mathematicians do best. We are going to think, calculate, and tell stories. Stories about how humans first tried to make sense of time, how math crept into the picture, and how some very clever people ended up writing equations that bend the rules of reality. It sounds complicated, but don't worry, I will tell it to you slowly like a bedtime story, and I will make jokes because if you are going to wrestle with Einstein, Gödel, and wormholes, you need humor like oxygen. So let's start with the obvious question. What even is time? Have you ever tried to define it? It's trickier than you think. Time is one of those things that everybody knows until you ask them to explain it, and then suddenly people sound like confused philosophers at 3 a.m. Even St. Augustine once said, "What then is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know." That was in the 4th century, and honestly, not much has changed since then. But long before philosophers sat around and stressed about it, regular humans already had to deal with time. Imagine being one of the first humans. You notice the sun rises, the sun sets, there are seasons. If you plant seeds at the wrong time, you starve. Congratulations, you have just discovered the most terrifying boss of your life, time itself. You cannot see it, you cannot hold it, but you are ruled by it. The ancient Greeks were among the first to really try to put words to this slippery thing. And of course, because they were overachievers, they did not just invent one concept of time. They invented two, chronos and kairos. Chronos was time as we normally think of it, the ticking of a clock, seconds marching in order like soldiers. Kairos, though, was something else entirely. Kairos meant the right time, the opportune moment. Time not as a measurement, but as a feeling, like when you know it is the perfect time to tell a joke, or the worst time to text your ex. That was kairos. Already you can see how messy this is. Time is not just one thing. It is measurement, it is memory, it is feeling. And as humans got smarter, or at least more annoying, they started asking even bigger questions. Is time something that exists independently of us? Or is it just a trick of our perception? If all the clocks in the world stopped tomorrow, would time still exist? These are not just stoner questions, they are at the heart of mathematics and physics. But before math joined the party, mythology had a go at it. Ancient stories are packed with time tricks. In the Hindu epic Mahabharata, a hero visits the gods and spends what he thinks is a short stay, only to return and find that centuries have passed on Earth. In Japanese folklore, there is the story of Urashima Tara, a fisherman who visits an undersea palace for a few days. When he returns, 300 years have gone by. And of course in the West we have Rip Van Winkle, the man who fell asleep and woke up decades later to find the world completely changed. These stories show something important. Humans have always wanted to escape time, to bend it, to cheat it. We hate that it is always pushing us forward. One way only, no refunds, no rewinds. We wanted to slip out of the current. And the idea that you could go back or forward faster was just too irresistible not to imagine. But back then it was just imagination. No math yet. Just myths, dreams, and maybe a few mushrooms involved. And then along came Isaac Newton, who decided to take the whole thing far too seriously. For Newton, time was absolute. It was this universal clock ticking away, the same for everyone, everywhere, forever. He imagined the universe as a giant machine, a clockwork. You wind it up, and the gears move, and the hands tick, and everything follows neat mathematical laws. If you knew the position and speed of every atom at one moment, You could, in theory, calculate the entire future and the entire past, like some terrifying cosmic Excel spreadsheet. Of course, Newton had no idea that a few centuries later a man named Einstein would come along and say, "Nice work, but actually, time is stretchy spaghetti, and the universe is not a clock, it is more like a trampoline." But let's not get ahead of ourselves, we will get there soon enough. For now, I want you to notice the shift. Humans went from telling stories about fishermen in magical palaces to writing equations that could predict the motion of the planets. And slowly, math started to whisper that time was not just a mystery, it was something you could put into symbols, equations, numbers, geometry, and that is where things started to get dangerous, because once you can describe something in math, you can also start to bend it. So as you lie there listening, maybe starting to feel your eyes get heavy, I want you to remember this. You are not just drifting off to sleep, you are drifting through time, second by second, a small, steady journey into the future, no DeLorean required. The only machine you need tonight is your own imagination, guided gently by mathematics. And when you wake up tomorrow, don't be surprised if you feel like you have travelled in time, because in a way you have. And trust me, the math of it only gets stranger from here. So here's the thing. You and I are both moving through time right now. Every second, another one slips behind us, like cars on a highway you can never drive back onto. But let me ask you something. What exactly are we moving through? What even is time? This is one of those questions that seems easy until you actually try to answer it. Like, what is water? Easy. It's the wet stuff you drink. But time? Try explaining that one at a dinner party, and see how fast people start pretending they need to use the bathroom. The ancient Greeks, being professional overthinkers, gave it a serious shot. They even came up with 2 words for time because of course they did. First there's chronos. That's the time you know from your watch or your phone. The kind of time that just keeps going, tick-tock, tick-tock. It's the boring, reliable time that makes sure your Zoom meeting starts at 9 a.m. sharp, whether you want it to or not. Chronos is the universal background music of existence. But then they had kairos, which is not about clocks at all. Kairos means the right time, the opportune moment. The feeling that now is the perfect time to act, or maybe the worst time to act, depending on the situation. Imagine you are standing in front of your crush and you think, should I confess my feelings? Chronos doesn't care, it's just another second, but Kairos leans over and whispers, yes, this is the moment, or more often, no, please, absolutely not, run. So from the very beginning, humans couldn't decide, is time a number you measure, or is it something you feel? And that confusion has stuck with us ever since. Now let's jump a bit forward in history. Fast forward to the Middle Ages, when St. Augustine was sitting around, probably trying to avoid answering emails, and he wrote something very honest. What then is time? If no one asks me, I know. If I wish to explain it to him who asks, I do not know. That's the 4th century version of It's Complicated. Which is funny, because thousands of years later, physicists are still basically saying the same thing. But okay, let's get practical. Imagine you're waiting at the DMV. 10 minutes feels like 10 hours. Now imagine you're playing your favourite video game. 10 hours feels like 10 minutes. Objectively, both were the same amount of chronos. But subjectively, the kairos was completely different. That's because our brains are terrible timekeepers. You could say we are running on the worst clock in the universe, which is both tragic and kind of hilarious. Now, because humans hate not understanding things, we started inventing ways to measure time. First we watched the sun and the stars, then we built sundials, then water clocks, then hourglasses, then mechanical clocks, and eventually atomic clocks that are so precise that if you ran one for the entire age of the universe, it would only be off by about 1 second. That's right. While you're still trying to microwave popcorn without burning half the bag, physicists have built clocks that almost never mess up. But even with all that measuring, we still don't know what time is. Is it a real thing out there in the universe, like space or mass? Or is it just a concept, a way for our brains to organize events, so that breakfast doesn't happen after dinner? This is where Newton comes in. Isaac Newton, our favorite Apple enthusiast, looked at the world and said, time is absolute. It flows the same for everyone. Everywhere, always. If a second passes for you, the exact same second passes for me. For the sun, for the stars, for that weird neighbour who always mows the lawn at 6 a.m. Time, to Newton, was like a giant invisible river. We were all just floating on it together. And honestly, that made sense. The sun rose, the sun set, pendulums swung back and forth, clocks ticked. It all felt solid, reliable, comforting. But then, of course, Einstein showed up a few centuries later and ruined everything. He said, "Actually, time doesn't flow the same for everyone. It's not absolute. It depends on where you are and how fast you're moving." Which means Newton's nice orderly river turned out to be more like a jello mold, sticky, wobbly, and completely unfair. But I'll save the full Einstein drama for later chapters. For now, let's stay with the big philosophical view. Because here's the funny part. Even though math can model time in all sorts of ways and physics can measure it down to billionths of a second, none of that really helps you understand what time is. It's like describing a chocolate cake by writing down the exact chemistry of sugar molecules. Technically correct, but completely missing the point. And maybe that's the real reason time feels so slippery. Because unlike mass or length or volume, time is not something we can poke with a stick. It's something we only ever experience through change. If nothing ever changed, no movement, no aging, no sunrise, no heartbeat, you wouldn't even know time was passing. It would just be stillness, like a paused video. So maybe time isn't really a thing at all. Maybe it's just the way we describe change. Maybe it's the bookkeeping system the universe uses to keep track of cause and effect. Or maybe, and this is the spooky part, time is just an illusion, which sounds poetic until you realize it also means your alarm clock is gaslighting you. Of course, mathematicians couldn't leave it at that. They started building all kinds of clever ways to describe time in equations. Sometimes it was just a variable, like t. Sometimes it was part of geometry, bending and curving along with space. Sometimes it was a statistical arrow, pointing one way because entropy demanded it. And all of these models worked, but none of them told us why time feels the way it does. Here's a little fun fact. If you put two extremely precise atomic clocks side by side, they will tick in perfect harmony. But if you move one just a little bit higher than the other, say a few floors up in a tall building, the higher one will tick ever so slightly faster. Why? Because gravity affects time. So depending on where you're lying right now, your head is technically aging a tiny fraction faster than your feet. Congratulations, you are already experiencing time dilation, even in bed. Now, does that help us understand what time is? Not really, but it does make a good party fact. Assuming you go to parties where people enjoy hearing about time dilation, which, to be fair, is usually only other mathematicians, and maybe one very patient dog. So let's step back. Here is where we are so far. Humans have always felt time. We tried to describe it with stories, with myths, with words like chronos and kairos. We tried to measure it with clocks ever more precise. We tried to define it with philosophy. We tried to lock it into equations, and every time we think we've nailed it, time laughs at us and slips away again. But maybe that's okay. Maybe we don't need to completely understand time in order to live with it, or even in order to imagine traveling through it. After all, you don't need to know the chemical structure of a cloud to enjoy watching one drift by, and you don't need to solve the entire mystery of time to enjoy the thought that, somewhere out there, the math might let us jump around in it. So here's my advice. Don't stress too much about what time is. Nobody has figured it out yet. Not Newton, not Einstein, not the philosophers, not the atomic clocks. It's one of those mysteries we live inside of, and in a way that makes it the perfect subject for tonight. Because if we don't even know what time is, who's to say we can't play around with it? And that is exactly what we're going to do. From here on, we'll move past the definitions and into the stories, the math, and the strange experiments that hint that time might not be as rigid as we think. We'll look at dilation, bending, wormholes, paradoxes, and the wildest thought experiments you've ever heard. But first, maybe take a deep breath. Notice the second that just passed, and the next, and the next. That's time, whatever it is, slipping by, and together we're about to chase it. Humans are funny creatures. We can barely handle the present. We burn toast, we forget birthdays, we text the wrong person. And yet somehow we've always been obsessed with the idea of escaping the normal flow of time. Long before anyone wrote down equations or argued about relativity, people were already telling stories about slipping out of the river of time, about waking up in the wrong century, or about cheating death by jumping past it. If you look into the oldest myths and legends, time travel is everywhere. Maybe not with machines or math, but with gods, magic, and a lot of wishful thinking. Let's start in India, because they were ahead of the game by a couple thousand years. In the great Hindu epic, the Mahabharata, there's a story about King Kakudmi. He goes to visit the god Brahma to ask some questions. Maybe about marriage, maybe about life, who knows? The important part is that he waits while Brahma listens to some celestial music. For the king, it feels like a short visit. But when he finally returns to Earth, he finds that thousands of years have passed. Everyone he knew is gone. His kingdom is history. Imagine leaving home to buy milk and coming back to discover that humans have colonized Mars. That is time travel, ancient style. The same idea shows up in Japanese folklore. The story of Urashima Taro goes like this. A fisherman rescues a turtle which, as you do, turns out to be a magical turtle. The turtle takes him to the dragon palace under the sea, where he stays for what feels like just a few days. When he finally returns home, centuries have passed. His village is unrecognizable, his family long gone, and to really rub it in, he opens a mysterious box the princess of the sea gave him, and instantly turns into an old man. Talk about a bad souvenir. These stories are thousands of years old, and yet they sound exactly like modern science fiction. Heroes leave their normal world, step into a strange realm, and when they come back, the timeline has betrayed them. It's basically Interstellar without the budget for CGI. Western tradition has its own version. You probably know the story of Rip Van Winkle. He wanders into the mountains, meets some mysterious men who give him some drinks, falls asleep, and wakes up 20 years later. The world has changed. The American Revolution happened while he was napping, which is honestly the most relatable way to experience history. All these stories have the same theme. Humans can't resist the thought of skipping through time. Sometimes it's a reward, sometimes a curse. But it's always fascinating. Why? Probably because time is the one thing we can't control. You can fight against kings, you can argue with gods, you can even invent math to predict the stars, but you can't stop the seconds from marching forward. So we dreamed of loopholes. Now, here's the interesting part. These early stories were not just entertainment. They also showed how people were starting to think about time as something that could be bent. Not just a straight road, but something with shortcuts, hidden tunnels or magical elevators. It wasn't yet math, but it was imagination laying the groundwork. Before you can invent equations, you have to invent the idea. In fact, one of the earliest scientific ideas of time travel comes from the Greek story of the 7 sleepers of Ephesus. The legend goes that a group of Christian youths hid in a cave during Roman persecution, fell asleep and woke up centuries later to find Christianity legalized. The story spread across cultures, even into the Quran. So again, sleep as time travel, which, to be fair, is still the most affordable method we have today. But let's step back for a second. Notice something important. None of these early stories involve machines or equations. They involve gods, magic, dreams, or deep sleep. That's because for ancient people, time was not something you could calculate. It was mysterious, divine, something only higher powers could mess with. Humans didn't think they had the right tools. And honestly, they didn't. They didn't have algebra, calculus, or even good clocks. What they had were myths. And myths are just humanity's way of asking questions out loud. Here's a little side note. When you start digging into mythology, you realize people were already aware of something close to Einstein's relativity, without the math. They understood that time feels different depending on where you are. The fisherman under the sea, the king in heaven, the sleeper in the cave, they all experience time differently from the world outside. That's basically time dilation explained with turtles and gods instead of equations. Of course, not all time travel stories were tragic. Some were just plain weird. In Celtic legends, heroes wander into fairylands where time passes differently. Stay too long at the party, and when you come back, everyone you know is dust. The fairies apparently had really good DJs, because people always stayed too long. So why do all these stories end badly? Why do the time travelers always lose everything? Maybe it was a way to warn people. Don't mess with time. Don't skip your responsibilities. Don't try to cheat life. Or maybe the storytellers were just pessimists. But there's another possibility. Maybe deep down, people sense that playing with time is dangerous, because it messes with causality. If you can jump around in the timeline, then nothing is stable anymore. Actions lose their meaning. The whole system breaks down. Which brings us to a funny thought. Humans invented time travel stories before they invented working plumbing. Priorities, right? But that's what makes us human. We can't stop asking what if, even when we have no idea how to answer. Now, here's the connection to math. You might think these myths are just cute bedtime stories, but they planted seeds. By imagining time as flexible, as something you could bend or escape, humans were already preparing their minds for the day when equations would prove the same thing. When Einstein finally showed that time is relative, the world was shocked. But the myths, they'd been whispering it for thousands of years. So the next time someone tells you mythology is useless, remind them that ancient storytellers were basically the first science fiction authors, and their wild tales gave mathematicians permission to dream, because without the dreams, you never get the math. So let's sum this up. Humans have always hated being trapped in time. We dreamed of skipping centuries, of waking up in the future, of cheating the rules. We told stories about gods, palaces, caves, and fairylands. And even though we didn't know it, we were already poking at the same mysteries that modern physics is still wrestling with today. And honestly, isn't that kind of comforting? The idea that across thousands of years, across cultures, people have all shared the same wish, to escape the relentless tick-tock of Chronos, to find Kairos, the perfect moment where time feels different, to slip, even just for a while, out of the ordinary flow. Now, of course, today we don't use turtles or caves. We use equations, telescopes, and really expensive particle accelerators. But the dream is the same, and in the next part of our journey, we'll meet the man who first tried to take that dream out of the world of myth and into the world of math. His name was Isaac Newton, and to him, time wasn't flexible at all. It was absolute, solid, a perfect clock that never wavered. But as we'll see, Newton's clockwork would eventually get smashed to pieces by Einstein's relativity. And that, my friend, is when the math of time travel really begins. Alright, so humanity had spent thousands of years telling dreamy stories about gods, turtles, and people who accidentally overslept by a few centuries. Cute, yes. Scientific, not so much. Then along came Isaac Newton, who basically looked at all that mythology and said, okay, enough fairy tales. Let's actually figure out how the universe works. Newton is one of those names you hear so often that it stops meaning anything. He's like the Beyoncé of mathematics. Drop his name and everyone nods. But if you ask what he actually did, most people just mumble something about an apple, which, by the way, yes, the apple story is at least partly true. But it wasn't like Newton was just sitting under a tree when an apple bonked him on the head and boom, gravity. He had been obsessively thinking about motion and forces for years. The apple was just the world's most convenient metaphor. So what did Newton actually do? He looked at the chaos of nature. Planets moving, apples falling, tides rising, cannonballs flying, and said, I think I can describe all of this with math. And then he did, with 3 deceptively simple laws of motion and the universal law of gravitation. Newton turned the universe into one giant predictable machine. This is where the idea of the clockwork universe comes in. Newton imagined the cosmos as a perfect clock. The gears are the planets, the stars, the comets. The hands are the laws of motion. Time itself is the steady tick-tock driving it all forward, second after second, never faltering, never bending. In Newton's view, time was absolute. That means it was the same everywhere, for everyone, forever. A second for you was exactly the same as a second for me. If a planet orbited a star millions of light years away, its seconds were identical to ours here on Earth. No matter where you went, no matter how fast you moved, time was like an invisible river flowing steadily on. That idea felt natural because it matched human experience. You and your neighbor both look at your clocks and see the same time. 2 candles burn down in the same number of minutes. A pendulum swings back and forth rhythmically, so Newton's version of time was comforting, solid, and reliable. But here's where it gets juicy. If time is absolute and the universe is one giant machine, then in theory, if you knew the position and velocity of every single particle in the cosmos, you could calculate the entire past and the entire future. Every event, every choice, every sneeze, all predetermined by the cosmic clockwork. That's a terrifying thought, right? It basically means free will doesn't exist. You think you're choosing to eat pizza tonight, but really, the initial conditions of the Big Bang already decided that for you. You're just acting out the gears of Newton's clock. Of course, not everyone liked this implication. Some philosophers said, "Hold on, I don't want to live in a universe where I'm just a cog in a machine." But from a mathematical perspective, it was beautiful. Suddenly, the chaos of reality could be predicted. The planets were not wandering randomly. They followed precise calculable orbits. The apple didn't just fall, it followed a specific trajectory that you could plot on a graph. The tides, the moons, the comets, they all obeyed the same rules. This made Newton kind of a superhero of his time. People had been terrified of comets, for example. They thought they were omens of doom, signs of divine punishment. But Newton's math showed that comets were just objects obeying gravity, no divine wrath necessary, which is either comforting or really disappointing, depending on how dramatic you are. And let's not forget his invention of calculus. Newton basically invented an entirely new branch of mathematics, just so he could describe how things moved in time. That's right, he looked at the universe and thought, there's no math for this, guess I'll make some. Meanwhile, you and I get stressed about doing our taxes. So what does all this have to do with time travel? Well, Newton's model left no room for it. In a clockwork universe, time is fixed, universal, and one-directional. The hands of the clock only move forward. You can't skip around, you can't rewind, you can't jump ahead. The best you can do is make really accurate predictions about where the hands will be in the future. But the flow of time itself, totally out of your control. In fact, Newton's universe is the least sci-fi friendly universe ever. It's basically the opposite of Doctor Who. No wormholes, no paradoxes, just gears grinding away forever. Reliable, yes. Exciting, no. But here's the funny thing. For centuries, Newton's picture worked incredibly well. His equations were so accurate that we used them to predict eclipses, launch ships, build bridges, and eventually send rockets into space. Even today, if you want to calculate how a baseball flies through the air, or how to build a roller coaster that won't kill people, you use Newton's math. The only problem is that the universe doesn't always behave like a clock. Sometimes it gets weird, really weird, and Newton's model, perfect as it seemed, eventually started to crack. For example, astronomers noticed that Mercury's orbit around the Sun didn't quite match Newton's predictions. Just a tiny wobble, but enough to make them nervous. At first, people thought maybe there was another hidden planet tugging at Mercury, like a cosmic prankster. They even gave it a name, Vulcan. Spoiler alert, Vulcan does not exist. What was actually happening was that Newton's clockwork rules were not the whole story. Something deeper was going on. And that's where Einstein comes in, a couple hundred years later, and smashes the absolute time idea into a million pieces. But hold on, we'll get to him in the next chapter. For now, let's appreciate what Newton did. He gave humanity a framework where time was something you could plug into equations. He stripped away the gods and the myths and replaced them with math. That's a big step. Before Newton, time was mysterious. After Newton, time was a variable. T, that little letter, made the universe predictable. And yes, his model turned out to be incomplete, but that doesn't make it wrong. It's like saying a bicycle is incomplete because it can't fly. True, but it's still a fantastic way to get around. Newton's clockwork universe was humanity's bicycle, and eventually Einstein came along and built the jet plane. So next time you hear about Newton and his apple, remember that it wasn't just gravity he discovered, it was the idea that the entire cosmos could be explained like a giant machine ticking along in perfect order, a universe where time was universal and absolute. And if nothing else, it was the perfect setup for Einstein to come in later and say, "Actually, Isaac, time is stretchy spaghetti. But before we bend time, we have to break it." And that's exactly what Einstein did. If Isaac Newton saw the universe as a perfect ticking clock, Albert Einstein came along and smashed the clock with a hammer. He didn't mean to, exactly. He was just trying to understand how light worked. But in the process, he rewrote the rules of time itself. Einstein wasn't the stereotypical genius locked in a tower. He was more like the underdog of physics. As a young man, he couldn't even get a job as a professor. Instead, he worked in a patent office in Switzerland, spending his days stamping boring documents about inventions nobody remembers. Imagine the guy revolutionizing our understanding of the universe being paid to make sure a new kind of stapler was legally protected. But maybe that quiet job was a blessing. It gave him time to think, and think he did. In 1905, Einstein published 4 papers in 1 year, what scientists call his annus mirabilis, or miracle year. In those papers, he basically blew up physics as people knew it. One of his biggest insights was about light. Everyone knew light was fast, but just how fast? Scientists had measured it at about 300,000 kilometers per second. That's roughly 7 times around the Earth in 1 second. The crazy part? Einstein realized that no matter how fast you move, light always outruns you by the exact same speed. You could be jogging, driving, or riding a rocket, and the beam of light would still zoom away from you at 300,000 kilometers per second. Always. Without exception. This created a big problem, because if the speed of light never changes, then something else has to give. And what gives? Time. Einstein figured out that in order for the speed of light to stay constant, time itself must stretch or shrink depending on how fast you're moving. Suddenly, Newton's idea of absolute time was toast. Time was not universal anymore. It was relative, and that's where we get the name, the theory of relativity. Now, what does that mean in everyday terms? Here's an example. Imagine you have twins. One twin stays on Earth. The other hops on a spaceship, flies around near the speed of light for a while, and then comes back. When they reunite, the spacefaring twin will be younger than the Earth twin. Not because of moisturizer or good genetics, but because time literally moved slower for them while traveling fast. This is called time dilation, and it's not just science fiction, it's real. In fact, astronauts on the International Space Station experience a tiny bit of this every day. Because they're moving so fast around Earth, their clocks tick slightly slower than ours. We're talking milliseconds, but still it means technically astronauts are time travelers. They are living in the future just by a hair, which is the lamest but also coolest superpower ever. Free Botox courtesy of Einstein. But Einstein didn't stop there. In 1915, he came out with his general theory of relativity, which took things even further. He realized that gravity isn't just some invisible force pulling things together like Newton thought. Instead, gravity is the bending of space and time itself. Massive objects like planets and stars warp the fabric of reality, and that's why things fall or orbit. It's not that the Earth pulls you down, it's that Earth bends space-time, and you're just following the curve. Picture a trampoline with a bowling ball in the middle. If you roll a marble nearby, it will spiral toward the bowling ball, not because the ball is pulling it, but because the trampoline is warped. That's what space-time is like, except instead of a 2-dimensional trampoline, it's 4 dimensions being warped at once. And instead of a marble, it's literally everything in the universe. Now here's where it gets really wild. If space-time can bend, then time itself can bend, which means, at least in theory, you can manipulate it. Suddenly, time travel doesn't sound like just a fairy tale anymore. It sounds like math. Of course, this blew people's minds. Imagine being a physicist in 1915. You grew up believing the universe was a nice, predictable Newtonian clock, and then this guy with wild hair tells you, actually, time is stretchy, space is bendy, and your equations are wrong. That's like showing up to a Monopoly game and declaring, from now on the thimble piece can teleport. People were understandably confused. But the evidence piled up. In 1919, during a solar eclipse, scientists observed starlight bending around the sun exactly as Einstein predicted. Newspapers around the world announced Einstein overturns Newton. He went from obscure patent clerk to global celebrity overnight. People wrote songs about him, he got fan mail, he basically became the first rock star of science. So, what does this have to do with our journey tonight? Well, Einstein's relativity is the first real scientific foundation for time travel. It proves that time is not fixed. It stretches, it bends, it dilates. If you move fast enough or sit near something with enough gravity, you can experience time differently than everyone else, which is, let's be honest, extremely cool. Here's a fun fact. Your phone's GPS relies on this. The satellites in orbit experience both special relativity, because they're moving fast, and general relativity, because they're farther from Earth's gravity. Their clocks tick differently from yours. If engineers didn't adjust for this, your Google Maps would be off by several kilometers, which means relativity is the reason you can find the nearest Taco Bell. Einstein saving humanity one burrito at a time. Now, Einstein never built a time machine. He was too cautious for that. But his math opened the door. He showed that time is not a universal river flowing the same for everyone. It's more like a flexible fabric, twisting and stretching depending on the circumstances, And if you can stretch something, maybe you can tear it, maybe you can fold it, maybe you can sneak through it. Of course, Einstein himself was skeptical about wild time travel scenarios. He once joked that people would abuse it to go back and fix their math exams, but other physicists looked at his equations and thought, wait a minute, if space-time can bend this much, what's stopping us from creating loops? What's stopping us from actually traveling through time? That's where the story gets strange. From here on, relativity isn't just about explaining planets and stars. It becomes a playground for wormholes, paradoxes, and universes where time doesn't play by the rules. But we're getting ahead of ourselves. For now, here's what you need to remember. Newton gave us a clockwork universe with absolute time. Einstein smashed that clock and showed us that time is relative, flexible, and deeply connected to space itself. The universe isn't a machine, it's a trampoline. A wobbly, stretchy trampoline we're all bouncing on together. And if that doesn't make you want to build a time machine, I don't know what will. If Isaac Newton saw the universe as a perfect ticking clock, Albert Einstein came along and smashed the clock with a hammer. He didn't mean to. Exactly. He was just trying to understand how light worked. But in the process, he rewrote the rules of time itself. Einstein wasn't the stereotypical genius locked in a tower. He was more like the underdog of physics. As a young man, he couldn't even get a job as a professor. Instead, he worked in a patent office in Switzerland, spending his days stamping boring documents about inventions nobody remembers. Imagine the guy revolutionizing our understanding of the universe being paid to make sure a new kind of stapler was legally protected. But maybe that quiet job was a blessing. It gave him time to think. And think he did. In 1905, Einstein published 4 papers in 1 year, what scientists call his annus mirabilis, or miracle year. In those papers, he basically blew up physics as people knew it. One of his biggest insights was about light. Everyone knew light was fast. But just how fast? Scientists had measured it at about 300,000 kilometers per second. That's roughly 7 times around the Earth in 1 second. The crazy part? Einstein realized that no matter how fast you move, light always outruns you by the exact same speed. You could be jogging, driving, or riding a rocket, and the beam of light would still zoom away from you at 300,000 kilometers per second, always, without exception. This created a big problem, because if the speed of light never changes, then something else has to give. And what gives? Time. Einstein figured out that in order for the speed of light to stay constant, time itself must stretch or shrink depending on how fast you're moving. Suddenly, Newton's idea of absolute time was toast. Time was not universal anymore. It was relative, and that's where we get the name, the theory of relativity. Now, what does that mean in everyday terms? Here's an example. Imagine you have twins. One twin stays on Earth, the other hops on a spaceship, flies around near the speed of light for a while, and then comes back. When they reunite, the spacefaring twin will be younger than the Earth twin. Not because of moisturizer or good genetics, but because time literally moved slower for them while traveling fast. This is called time dilation, and it's not just science fiction, it's real. In fact, astronauts on the International Space Station experience a tiny bit of this every day. Because they're moving so fast around Earth, their clocks tick slightly slower than ours. We're talking milliseconds, but still it means technically astronauts are time travelers. They are living in the future just by a hair, which is the lamest but also coolest superpower ever. Free Botox courtesy of Einstein. But Einstein didn't stop there. In 1915, he came out with his general theory of relativity, which took things even further. He realized that gravity isn't just some invisible force pulling things together like Newton thought. Instead, gravity is the bending of space and time itself. Massive objects like planets and stars warp the fabric of reality, and that's why things fall or orbit. It's not that the Earth pulls you down, it's that Earth bends space-time, and you're just following the curve. Picture a trampoline with a bowling ball in the middle. If you roll a marble nearby, it will spiral toward the bowling ball. Not because the ball is pulling it, but because the trampoline is warped. That's what space-time is like. Except instead of a 2-dimensional trampoline, it's 4 dimensions being warped at once. And instead of a marble, it's literally everything in the universe. Now here's where it gets really wild. If space-time can bend, then time itself can bend. Which means, at least in theory, you can manipulate it. Suddenly, time travel doesn't sound like just a fairy tale anymore. It sounds like math. Of course, this blew people's minds. Imagine being a physicist in 1915. You grew up believing the universe was a nice, predictable Newtonian clock, and then this guy with wild hair tells you, actually, time is stretchy, space is bendy, and your equations are wrong. That's like showing up to a Monopoly game and declaring, from now on, the thimble piece can teleport. People were understandably confused. But the evidence piled up. In 1919, during a solar eclipse, scientists observed starlight bending around the sun exactly as Einstein predicted. Newspapers around the world announced Einstein overturns Newton. He went from obscure patent clerk to global celebrity overnight. People wrote songs about him, he got fan mail, he basically became the first rock star of science. So what does this have to do with our journey tonight? Well, Einstein's relativity is the first real scientific foundation for time travel. It proves that time is not fixed. It stretches, it bends, it dilates. If you move fast enough or sit near something with enough gravity, you can experience time differently than everyone else, which is, let's be honest, extremely cool. Here's a fun fact. Your phone's GPS relies on this. The satellites in orbit experience both special relativity, because they're moving fast, and general relativity, because they're farther from Earth's gravity. Their clocks tick differently from yours. If engineers didn't adjust for this, your Google Maps would be off by several kilometers, which means relativity is the reason you can find the nearest Taco Bell. Einstein saving humanity one burrito at a time. Now, Einstein never built a time machine. He was too cautious for that. But his math opened the door. He showed that time is not a universal river flowing the same for everyone. It's more like a flexible fabric, twisting and stretching depending on the circumstances. And if you can stretch something, maybe you can tear it. Maybe you can fold it. Maybe you can sneak through it. Of course, Einstein himself was skeptical about wild time travel scenarios. He once joked that people would abuse it to go back and fix their math exams. But other physicists looked at his equations and thought, wait a minute, if space-time can bend this much, what's stopping us from creating loops? What's stopping us from actually traveling through time? That's where the story gets strange. From here on, relativity isn't just about explaining planets and stars. It becomes a playground for wormholes, paradoxes, and universes where time doesn't play by the rules. But we're getting ahead of ourselves. For now, here's what you need to remember. Newton gave us a clockwork universe with absolute time. Einstein smashed that clock and showed us that time is relative, flexible, and deeply connected to space itself. The universe isn't a machine, it's a trampoline, a wobbly, stretchy trampoline we're all bouncing on together. And if that doesn't make you want to build a time machine, I don't know what will. So far we've talked about time as if it's this slippery thing you can stretch and slow down. But to really understand how wild it gets, you have to see time as part of a bigger picture, because Einstein didn't just tell us that time is relative. He told us that time and space are actually the same thing. Let that sink in for a second. Time and space. The two things you thought were completely different, one you measure in seconds, the other in meters, turn out to be married. They're not just pen pals, they're full-on life partners. And together they make something called space-time. Now, space-time isn't something you can see or touch. You can't go to IKEA and buy a rug of space-time, though I'm sure it would sell out instantly. It's a mathematical concept. Think of it as the stage on which the universe plays out. Every particle, every planet, every galaxy, even you lying in bed right now, exists inside this four-dimensional fabric. 3 dimensions of space, length, width, height, and one of time. Put them together, and you've got the stage for everything. But here's the twist. Space-time isn't flat. It bends, it curves. Massive objects like stars and planets warp it. And when it bends, weird things happen. Light curves, time slows, gravity is just geometry pretending to be a force. Suddenly, the universe is less like a rigid machine and more like a cosmic waterbed. Okay, let's visualize this. Picture a giant trampoline stretched tight. That's space-time. Now put a bowling ball in the middle. The trampoline sags. That's what a planet or star does. It bends the fabric. If you roll a marble near the bowling ball, it curves inward, spirals around, maybe even falls in. That's gravity. Not a mysterious pulling force, just geometry. Einstein's genius was realizing that what we call gravity, is really the result of objects following curves in space-time. Earth isn't being pulled by the sun, it's just rolling along the curved fabric around the sun, like a marble on that trampoline, which, if you think about it, is way cooler than Newton's invisible force. Now, here's where time sneaks back in, because if space-time bends, time bends too. Imagine that trampoline again. If you stand on the slope near the bowling ball, it takes you longer to climb back up. That's kind of what happens to time near a massive object. The deeper you go into the curve, the slower time flows compared to someone far away. That's gravitational time dilation. Geometry itself is telling clocks how fast to tick. This might sound abstract, but it has real consequences. Remember the GPS satellites we talked about earlier? They're orbiting farther from Earth's gravity, which means their clocks tick faster than ours. Meanwhile, their speed also slows time down for them. Engineers literally have to correct for both effects at once. If they didn't, your navigation would be garbage. You'd ask for directions to the grocery store and end up in another state. The guy who first formalized this space-time idea was Hermann Minkowski, one of Einstein's old professors. He said, henceforth space by itself and time by itself are doomed to fade away into mere shadows. Only a kind of union of the two will preserve an independent reality. Translation, forget thinking about space and time separately. They're one thing, and once you accept that, all the strange effects we've been talking about, time dilation, bending light, warped gravity, suddenly make sense. But geometry doesn't just explain what we see. It also opens the door to some seriously weird possibilities. Because if space-time can bend, can it fold? Can it twist into loops? Can it tear? Suddenly the math isn't just describing the universe. It's suggesting that the universe might allow shortcuts, and shortcuts in space-time are another way of saying time travel. Here's an example. Imagine drawing two dots on a piece of paper, far apart. If you want to go from one dot to the other, you trace a long line across the page. But if you fold the paper so the two dots touch, you can just poke a hole through and jump across instantly. That's the basic idea of a wormhole, a shortcut through space-time. It's geometry gone rogue. We'll talk more about wormholes later, but the important thing here is that the math of space-time allows them. They're not just science fiction inventions, they're solutions to Einstein's equations. Whether they actually exist in the real universe is another question, but the fact that they're possible on paper is enough to keep physicists awake at night. Another strange idea is the light cone. This is how mathematicians map out what parts of the universe you can influence. Imagine you're standing in space-time, and you shine a flashlight. The light spreads out in a cone shape into the future. Everything inside that cone is reachable. Everything outside it, off limits. No signal, no matter how fast, can escape your cone. This is why the speed of light is the ultimate speed limit. It's geometry saying, nope, you can't cheat. But if space-time can curve enough, those cones can tilt. And in some extreme cases, they can even loop back on themselves. That's when time starts behaving very strangely indeed. That's when you get solutions that look like closed time-like curves. Basically, mathematical paths that bring you back to your own past. But we'll save that for later, because paradoxes deserve their own chapter. For now, the takeaway is this. The universe is not built on force. It's built on geometry. And that geometry doesn't just shape where objects move, it shapes how time itself flows. Think about how crazy that is. Math isn't just describing the universe, it is the universe. The difference between you aging normally and you aging slower isn't magic, it's the shape of space-time under your feet. Here's a fun little twist. Even empty space isn't really empty. Quantum physics tells us that even the vacuum is bubbling with fluctuations, particles popping in and out of existence. That means space-time is alive, restless, dynamic. It's not just a blank stage, it's more like a trampoline where kids are constantly jumping on the corners, bouncing everything else around. No wonder time feels unstable. So let's bring this back to our bedtime story vibe. You're lying there, drifting through the quiet of the night, and all around you space-time is stretching, bending, wobbling. Your bed, your house, your planet, your galaxy, all of it rolling along this invisible fabric. And the ticking of your clock is not absolute. It's being whispered to by geometry itself. If that doesn't make you feel small and strangely cozy at the same time, I don't know what will, because here's the comforting part. No matter how complex the equations get, it all comes back to geometry, shapes, curves. The stuff you doodled in the margins of your math homework. Except now, those shapes decide the fate of time. So next time you think math is boring, remember this. The universe is literally a giant geometric playground. And in that playground, time is not a dictator. It's just another player. And that realization is exactly what opens the door to the next chapter, wormholes. Or, as I like to call them, Einstein's accidental time machines. Alright, so we've bent time, we've curved space, and we've realized that the universe is basically a trampoline with bowling balls and marbles rolling around. But what happens if you take that trampoline and fold it? What if you punch a hole straight through it? Welcome to the bizarre world of wormholes. Now, the idea of wormholes wasn't something Einstein set out to discover. He wasn't lying in bed thinking, wouldn't it be cool if people could travel through shortcuts in space-time? No, he was trying to solve equations. But as often happens in math, sometimes the equations have solutions that nobody expected. And one of those solutions looked like a tunnel, what we now call a wormhole. Here's the basic picture. Imagine space-time as a giant sheet of paper. If you draw two dots on opposite ends, the straight line between them is the normal route. That's how light travels, how rockets travel, how everything travels if you obey the rules. But what if you fold the paper so the two dots touch? Suddenly, you can just poke a hole and jump across instantly. A shortcut. That's what a wormhole is supposed to be. A tunnel through space-time connecting two distant points. Einstein and his colleague Nathan Rosen first described these mathematical tunnels in the 1930s, so the earliest ones were called Einstein-Rosen bridges. They weren't thinking about interstellar travel or Doctor Who, they were just following the math of general relativity, and the math said space-time could allow bridges. The catch? Those early solutions collapsed instantly. Imagine trying to build a tunnel out of jello. The walls cave in before you can even step inside. In other words, Einstein's wormholes were more like blink-and-you-miss-it tunnels. Not very practical if you're trying to pop over to Alpha Centauri for lunch. But that didn't stop people from dreaming. Physicists kept poking at the equations, and science fiction writers went absolutely wild. Wormholes became the go-to explanation for faster-than-light travel in movies and books. Forget warp drive, just hop in a wormhole and pop out in another galaxy. Easy. Now here's where things get fun for us. Sleepless mathematicians. Wormholes might not just connect 2 points in space. They might also connect 2 points in time. That's right. Wormholes are the first serious contenders for real-time machines. How would that work? Picture this. You have a wormhole with two ends, let's call them A and B. Normally, you could step in at A and walk out at B. But now imagine you move one end of the wormhole really fast, close to the speed of light, and then bring it back. Thanks to time dilation, the moving end ages slower than the stationary one, which means now the two ends are out of sync. Walk through one and you don't just pop out somewhere else in space, you pop out at a different time. Congratulations, you've just built a time machine with math. Sounds perfect, right? Unfortunately, reality is not that generous. Wormholes, if they exist, would require something called exotic matter to stay open. Exotic matter is basically stuff with negative energy density. And no, we don't have any in stock. It's the kind of matter that doesn't behave like anything we've ever seen in the lab. Without it, wormholes snap shut before you can say flux capacitor. Still, physicists like Kip Thorne, the guy who consulted on Interstellar, took this seriously enough to write actual papers on traversable wormholes. And Hollywood loved it. When you see people in movies stepping into glowing tunnels and ending up across the universe, you can thank Einstein's equations for planting that seed. But wormholes aren't just pop culture candy, they're also riddled with paradoxes. If you can connect 2 points in time, you immediately get all the classic time travel headaches. The grandfather paradox, causality loops, universe-breaking contradictions. It's like opening a restaurant where the menu is just chaos. Here's a funny thought. Wormholes might exist all around us, but they could be microscopic. Quantum fluctuations could be constantly creating tiny wormholes that appear and disappear faster than we can detect. They'd be too small to crawl through, of course, unless you happen to be an electron with vacation plans. But if we ever found a way to stabilize them, who knows? And let's not forget the energy requirements. To make a wormhole big enough to walk through, you'd need more energy than exists in the entire observable universe, which is kind of a deal breaker. It's like saying, sure, you can time travel, you just need to buy every battery on Earth and then some. Still, wormholes hold a special place in physics because they show how weird relativity really is. Einstein gave us equations, and the equations gave us tunnels that connect distant regions of space-time. Nobody asked for them. They just popped out of the math, like a cosmic Easter egg. Let's be honest, too. Wormholes are fun to imagine. Everyone loves the idea of stepping through a door and instantly being somewhere or someone else. They scratch that human itch for shortcuts, for skipping the boring parts of the journey. We're the species that invented elevators because stairs were too slow. Of course we want wormholes. So where does that leave us? Right now, wormholes are purely theoretical. They might not exist at all, or they might be tiny and unstable, or they might require physics we don't understand yet. But the fact that they could exist according to the math is enough to make them one of the most tantalizing ideas in science. And maybe that's the real lesson here. Math doesn't just describe what we already see. Sometimes it describes things we've never seen, things that might not even exist, but things that still capture our imagination. Einstein never built a wormhole, but his equations inspired generations of physicists, writers, and sleepless thinkers to wonder, what if? So next time you see a wormhole in a movie, remember that it's not just a special effect, it's the ghost of Einstein's equations, whispering that maybe, just maybe, the universe has shortcuts hidden in its geometry. And speaking of strange possibilities, there's one mathematician who took relativity even further. His name was Gödel, and he found a solution to Einstein's equations where time didn't just bend, it looped. As in, you could literally circle back into your own past. But Gödel being Gödel, the story is a little weirder than that. By now, you're probably thinking, okay, Einstein bent time. Wormholes might connect distant points. This is already strange enough. But then along came Gödel, and he looked at Einstein's equations and basically said, "You think that's weird? Hold my coffee." Gödel is one of the most fascinating characters in all of mathematics. He's famous for his incompleteness theorems, proofs that showed math can never be fully complete or fully consistent. Which, to put it simply, is like saying, no matter how many rules you write down, there will always be truths that escape them. That alone would have guaranteed him a spot in the Genius Hall of Fame. But Gödel was also eccentric. He was shy, paranoid, and constantly worried about being poisoned. He trusted almost no one except his wife, who ended up preparing all of his meals. Later in life, when she became too ill to cook, Gödel basically stopped eating and starved to death. Dark, yes, but it shows you the kind of mind we're dealing with. A man brilliant enough to break mathematics, but fragile enough to be broken by his own fears. Now, what does Gödel have to do with time travel? Well, he was a close friend of Einstein's. They would take long walks together at Princeton, discussing the nature of reality like two philosophers with unlimited patience. And while Einstein was busy becoming a scientific celebrity, Gödel was quietly tinkering with relativity. In 1949, Gödel dropped a bombshell. He found an exact solution to Einstein's field equations that described a bizarre kind of universe. Not a universe like ours, filled with galaxies expanding outward, but a universe that rotated, the whole cosmos, spinning. And in this rotating universe, something very strange happened. Time didn't behave normally. Gödel's math showed that in his universe you could trace a path through space-time that looped back onto itself. Imagine walking forward but eventually ending up at the same point where you started. Not in space, but in time. These were called closed time-like curves. And what they meant was simple and terrifying. In Gödel's universe, time travel to the past was possible. Think about that. One of the most rigorous, careful logicians in history took Einstein's equations and found they allowed for a cosmos where you could literally circle back to yesterday. No magic, no turtles, just math. Einstein's reaction? He was unsettled. He admired Gödel, but he didn't love the idea that his beautiful equations allowed time loops. He even worried that Gödel's discovery made relativity look absurd. If the math said time travel was possible, what did that mean for causality, for free will, for sanity itself? Gödel, of course, didn't mind. He actually thought his rotating universe was a clue that time itself might be an illusion. To him, the fact that you could mathematically erase the distinction between past and future meant that the flow of time was something our minds invented, not something real in the universe. Time wasn't a river. It was more like a frozen block of ice, and our consciousness just slid across it, giving us the feeling of flow. This idea is sometimes called the block universe. In a block universe, the past, present, and future all exist at once. You don't move through time. Time is already there, laid out like a book you can flip through. That's a comforting thought if you hate surprises, and a terrifying thought if you like to believe you control your own destiny. But here's the kicker. Gödel's rotating universe doesn't actually describe our universe. Observations show that our cosmos isn't spinning the way his equations required. So we're safe for now from living in a literal time loop. But the fact that relativity allows such solutions is what keeps physicists awake at night. If the math says closed time-like curves are possible, who's to say they don't exist somewhere somehow? Of course, the paradoxes show up immediately. If you can loop back into your own past, you can meet your younger self. You can buy Bitcoin in 2009. You can accidentally stop your parents from meeting, which, inconveniently, would also stop you from existing, which would stop you from traveling back, which, well, you see the problem. The grandfather paradox is just the tip of the iceberg. Gödel's math opened Pandora's box, and inside were paradoxes stacked like Russian dolls. But Gödel wasn't the type to panic about paradoxes. He actually leaned into them. He thought they were proof that time itself wasn't what we thought it was. If you could make logical contradictions just by assuming time flows forward, maybe the problem wasn't the math. Maybe the problem was our assumption. Maybe time doesn't flow at all. That's a very Gödel thing to say. He loved turning assumptions upside down. It's like someone saying, look, we can't solve this crossword puzzle, and Gödel replying, that's because it's not a crossword puzzle, it's a Sudoku, and you've been holding it upside down. So what do we do with Gödel's universe? On one hand, it's a mathematical curiosity, a weird side road in relativity that doesn't match our observations. On the other hand, it's a warning sign. It shows that relativity, for all its brilliance, doesn't always behave the way we expect. The equations are powerful, but they don't come with a safety manual. Sometimes they spit out answers that sound like science fiction. And honestly, that's part of the magic. The universe is under no obligation to make sense to us. If the math says time loops are possible, we can't just dismiss it because it makes us uncomfortable. We have to wrestle with it, just like Gödel did. So next time you imagine traveling back to your childhood or visiting ancient Rome, remember one of the greatest logicians in history actually found a universe where that's not just a fantasy, it's baked into the structure of reality. And while Gödel's universe might not be ours, the idea of closed time-like curves stuck. Other physicists began to wonder, are there other ways to make time loop? Could rotating black holes or giant cylinders of matter, or even quantum effects create similar pathways? Suddenly, Gödel's strange thought experiment turned into a whole field of research. Which brings us to our next chapter, the paradoxes themselves. Because once you open the door to time loops, you also invite every logical headache in existence. From grandfathers who vanish to universes that collapse under their own contradictions. The problems pile up fast. And if you thought standing in line at the DMV made time feel weird, just wait until you see what happens when time literally ties itself in knots. Alright, let's talk about the problem that ruins every time travel story faster than you can say Back to the Future. The grandfather paradox. You've probably heard of it, but let's unpack it properly, with a little humor, because otherwise it will melt your brain. The idea is simple. Imagine you build a time machine. You travel back in time to when your grandfather was young before he met your grandmother. For reasons best not explained, you're having a bad day. Maybe he ate the last cookie. You prevent him from ever having children. Uh-oh, that means your parent never gets born. Which means you never get born. Which means you can't travel back in time to stop him in the first place. Which means he does live, has kids, and you're born, and then you see the loop. It's a cosmic-level family drama with no exit. This paradox is the poster child for why people freak out about backward time travel. Because it breaks causality, the basic rule that causes happen before effects. If you can mess with the past, the whole chain of cause and effect collapses like a badly stacked Jenga tower. But here's the thing, the grandfather paradox is just the most famous version. There are lots of paradoxes like this. Let's meet a few of them. First up, the bootstrap paradox. This one is sneakier. Imagine you love Beethoven's Fifth Symphony. You build a time machine, go back in time, and hand Beethoven the sheet music because you want to hear him play it live. But here's the twist. What if Beethoven never actually wrote it? What if the only reason he knows the symphony is because you gave it to him. Where did the music come from originally? It just exists in a loop, with no true creator. That's the bootstrap paradox. Something comes from nowhere. It's like plagiarizing yourself across centuries. Or take the information paradox. Imagine a scientist in the future writes down the solution to some impossible math problem. She then travels back in time and gives it to a younger self, who publishes it. Future generations learn it, she grows up, learns it, travels back, you get the point. The knowledge exists, but it was never invented. Who actually solved the problem? Nobody. Or maybe everybody. Depends how you look at it. Then there's the predestination paradox. This one is extra cruel. Imagine you try to go back in time to stop something bad from happening. You think you're changing history, but in trying to prevent it, you accidentally cause it. You're not changing the past, you're fulfilling it. It's like Oedipus trying to avoid his fate, only to run straight into it. Basically, time laughs in your face and says, "Nice try." Now the obvious question is, are these paradoxes fatal to the idea of time travel, or just weird puzzles we haven't solved yet? Some physicists argue that paradoxes are proof backward time travel is impossible. Stephen Hawking even proposed something cheekily called the chronology protection conjecture. Translation: the universe has a rule book, and one of the rules is that it hates paradoxes, so if you ever try to make one, reality will stop you, which sounds very comforting, like the cosmos has its own bouncer at the door of time saying, "Sorry, no causal loops allowed." Other scientists, though, say maybe paradoxes don't mean time travel is impossible. Maybe they just mean the universe works differently than we expect. One idea is the many worlds interpretation. This says that every time you change the past, you don't rewrite your own timeline, you just spin off a new one. Kill your grandfather and you don't erase yourself. You just end up in a timeline where you never existed, while the original you still exists in the old one. Problem solved, sort of. The paradox disappears, but at the cost of creating infinite alternate universes, which is cool if you're into sci-fi, but also kind of a cosmic paperwork nightmare. Another possibility is that the universe is self-consistent. This is called the Novikov self-consistency principle. It says, yes, time travel might be possible, but you can never actually create a paradox. Everything you do in the past was always part of history. If you go back and try to kill your grandfather, something will stop you. A gun jams, you trip. You suddenly realize you don't even know which man is your grandfather. Whatever happens, the timeline protects itself. You can interact with the past, but you can't change it. It's history with built-in insurance. Now, from a storytelling point of view, paradoxes are amazing. They make great movies, books, and bedtime thought experiments. But from a mathematical point of view, they're like flashing red warning signs. They tell us if time travel exists, it has to obey rules we don't fully understand yet. Otherwise, reality would collapse under the weight of contradictions. Here's a fun little anecdote. In 2009, Stephen Hawking actually threw a party for time travelers. He set up champagne, hors d'oeuvres, balloons, the whole deal. But he didn't send out the invitations until after the party was over. That way, only people from the future could attend. Guess what? Nobody showed up. Hawking joked that it was experimental proof that time travel into the past is impossible. Or maybe the time travelers just thought his party snacks weren't good enough. So where does that leave us? On the one hand, paradoxes are a huge problem for backward time travel. They break causality, they create impossible loops, and they make mathematicians want to bang their heads against chalkboards. On the other hand, the fact that the equations of relativity allow for time loops at all is still fascinating. Maybe paradoxes are just telling us we need a new framework, something beyond our current understanding of physics. And honestly, isn't that kind of the point? Paradoxes aren't just headaches, they're signposts pointing toward deeper truths. Every time humanity has run into a paradox, whether in math, in logic, or in physics, it has forced us to rethink our assumptions. Maybe time travel paradoxes are the universe's way of saying, you're close but not quite there yet. So the grandfather paradox and its cousins remind us that time is not simple. It's not just seconds marching forward. It's a web of cause and effect, fragile and mysterious. And if we tug too hard at the web, we risk tearing it. But paradoxes don't stop people from trying. Physicists have come up with some wild mathematical models of universes where time loops are possible without breaking reality. Cylinders of infinite matter, rotating black holes, even quantum tricks that let you cheat causality without technically breaking it, which means our journey is about to get even stranger. Because if you thought family drama was bad, wait until you meet something called closed time-like curves. These are the mathematical loops in space-time where you don't just risk erasing your grandfather, you risk erasing yourself in ways that make soap operas look tame. Alright, buckle up, or actually don't. You're lying in bed. Just get cozy, because things are about to get mathematically loopy. Literally. We're talking about something called closed time-like curves, or CTCs if you want to sound like a cool physicist at a party. These are among the strangest predictions to come out of Einstein's relativity, and if they exist, they would be the ultimate cosmic loophole, a way to travel back in time. Let's break down the name first. Time-like means a path through space-time that a normal object, like you or me, could actually follow. You can't move like a photon, but you can move like a human with mass. That's time-like. Closed means the path loops around and reconnects with itself. Put that together and you get a closed time-like curve, a path where you move forward in time, step by step, and eventually end up back where you started in your own past. Sounds impossible, right? But the equations allow it. Not always, and not everywhere, but under certain exotic conditions. Relativity says you can have loops in time, and once you have a loop, you have all the paradoxes we talked about in the last chapter, plus about 1,000 new headaches. The first person to really explore this was of course Gödel with his rotating universe. In his solution, the whole cosmos spun in such a way that time itself looped back. But Gödel wasn't alone. Other physicists started finding their own versions of time loops hiding in the math. One famous example is the Tipler cylinder, proposed by Frank Tipler in the 1970s. Imagine an infinitely long, super dense cylinder spinning at nearly the speed of light. The math suggests that if you travel around it in just the right way, space-time twists so much that you end up back in your own past. Boom, time loop. Of course, there's a small problem. Infinitely long isn't exactly something you can build in your backyard. You'd need an object longer than the observable universe, which is not great news for aspiring DIY time travelers. Another example comes from rotating black holes, also known as Kerr black holes. These are theoretical black holes that don't just sit there, they spin, and the math says that inside them, space-time could form closed time-like curves. The catch? To get there, you'd have to dive past the event horizon, where not even light escapes, and survive the most extreme environment in the universe. So, good luck with that. Then there are wormholes, which we talked about earlier. Some solutions suggest that if you drag one end of a wormhole around at near light speed, you can create a time difference between the two ends. Walk through, and you've got yourself a time loop. The universe's weirdest revolving door. Now, here's where things get interesting. Physicists have tried to imagine what life would be like inside a closed time-like curve. Suppose you step into one. From your perspective, you're just walking forward in time like normal. But after a while, you start noticing that events are repeating. You bump into your younger self. You drop your keys and pick them up again, over and over. You're trapped in a loop. Some versions of this sound like a nightmare, an eternal Groundhog Day. Others are more flexible, letting you interact with the past. And that's where paradoxes creep back in. What if you change something? Do you create contradictions? Or does the universe force events to be self-consistent? This is where the Novikov self-consistency principle makes a comeback. According to Novikov, if closed time-like curves exist, the universe won't allow paradoxes. Whatever you do in the loop was always part of history. You can't kill your grandfather because history says he survived. You can't stop yourself from entering the loop because you already did. It's frustrating, but it keeps reality from collapsing. Still, not everyone buys that. Some physicists argue that if closed time-like curves exist, they could allow information to appear from nowhere. Imagine sending yourself the answer to a homework problem from the future. You ace the class, grow up, build a time machine, and send the answer back. Who actually solved the problem? Nobody. The solution just exists in a loop. That's the bootstrap paradox again, now baked into space-time itself. And if you think physicists are immune to the fun of this, you're wrong. They've written actual papers about whether closed time-like curves could be used to build computers that solve impossible problems instantly. Imagine a machine that sends its answer back to itself in time, so it never even has to do the calculation, which sounds amazing until you realize you've basically built a paradox-powered supercomputer. Of course, Stephen Hawking wasn't impressed. He argued that the universe probably has a chronology protection mechanism, a kind of cosmic firewall that stops closed time-like curves from forming. Maybe quantum effects destabilize them before they cause trouble. Maybe physics has a secret rule that says, no loops allowed. In other words, reality has its own neighborhood watch program, and time paradoxes are not welcome. But the fact remains, the math doesn't forbid closed time-like curves outright. They're not science fiction inventions, they're legitimate solutions to Einstein's equations. That alone is enough to make people wonder. So where does that leave us? On the edge of possibility. Closed time-like curves are like the universe winking at us, saying, maybe you can loop through time, but maybe not. They're the ultimate tease. Possible on paper, probably impossible in practice, but irresistible to imagine. And here's a comforting thought. Even if closed time-like curves don't exist in reality, they still serve a purpose. They force us to confront what time really is. They challenge our ideas about causality, free will, and even the meaning of past and future. And in doing so, they keep mathematicians, physicists, and sleepless YouTube narrators very busy. So the next time you feel like your day is repeating itself, remember, in some universes it might literally be true. You could be stuck in a loop, living the same moments again and again. And if that doesn't make you grateful for boring, linear time, I don't know what will. And speaking of weirdness, if you think relativity's time loops are strange, just wait until quantum mechanics enters the picture. Because when you mix time travel with Schrödinger's cat, parallel universes, and particles that refuse to behave, things go from weird to absolutely bonkers. By now we've bent time, stretched it, and even looped it. Einstein gave us relativity, Gödel gave us cosmic merry-go-rounds, and wormholes dangled the possibility of shortcuts. But if you thought that was weird, buckle up, because now we're bringing in quantum mechanics. And quantum mechanics makes relativity look like a polite cup of tea. Quantum mechanics is the science of the very, very small atoms, electrons, photons, the little building blocks of reality. And down there, the universe doesn't play by the rules you and I are used to. It's messy, unpredictable, and deeply rude to classical common sense. Let's start with the famous Schrödinger's cat thought experiment. You've probably heard of it. Imagine a cat in a box with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, the counter triggers, the poison is released, and the cat dies. If the atom doesn't decay, the cat lives. The catch? According to quantum mechanics, until you open the box and check, the atom is in a superposition, both decayed and not decayed, which means the cat is both alive and dead. At the same time, quantum physics, ruining pet ownership since 1935. Now, what does this have to do with time travel? Well, quantum mechanics has its own strange relationship with time. Particles don't move in neat, predictable paths like little billiard balls. Instead, they exist in fuzzy clouds of probability. And here's the kicker. Some experiments suggest that quantum processes might allow effects to influence causes. In other words, the future might affect the past. One idea is called post-selected teleportation. It sounds like science fiction, but it's an actual proposal from physicists. The idea is that you can set up a quantum system where particles are entangled, linked so that what happens to one instantly affects the other, even across distance. Then, by carefully post-selecting the outcomes you allow, you can effectively send information back in time. Not people, not spaceships, but data. Tiny quantum messages that seem to cheat causality. And before you dismiss it as wild speculation, here's a twist. Researchers have actually simulated small versions of this in labs. They've shown that under certain conditions, quantum systems behave as if they are interacting with their own past. Does this mean we can build a time-traveling cat? No. But it does suggest that time in the quantum world is less rigid than we thought. Another quantum idea is the many worlds interpretation. This one says that every time a quantum event could go one way or another, the universe splits. In one universe, the cat lives. In another, the cat dies. In one universe, you ate pizza tonight. In another, you nobly chose a salad. Every possibility happens somewhere. So, if you travel back in time and accidentally mess with history, say you step on a butterfly in ancient Egypt, you don't erase your own future. Instead, you just spin off a new universe where things unfold differently. That solves the grandfather paradox neatly. You don't kill yourself by changing the past, you just create a timeline where you never existed. It's tidy in a multiverse sort of way. Of course, the many worlds view comes with its own headaches. If universes are constantly splitting, there are now infinite versions of you out there making different choices. Somewhere there's a version of you who became a rock star. Somewhere else there's a version who never learned how to ride a bike. And yes, somewhere there's a version who stopped listening to this video 5 minutes in. Poor soul. Then there's the idea of quantum time crystals. No, not something you buy at a New Age store. These are theoretical systems that repeat themselves in time, not just in space. Imagine a structure that changes, then cycles back forever, without using energy. It's like a perpetual motion machine, but for time. Some physicists think these could exist at the quantum level, and if so, they might offer clues about how time could be manipulated. And if you really want your brain to hurt, there's quantum entanglement. Two particles, separated by light years, can behave as if they're connected instantly. Einstein called it spooky action at a distance, because even he thought it sounded ridiculous. But it's been proven experimentally, again and again. What happens to one particle affects the other, faster than light should allow. It's not time travel in the classical sense, but it does suggest that our ideas of time and distance are. Here's a fun anecdote. In 2013, researchers performed an experiment where they teleported the state of a particle, not its physical body, across a distance using entanglement. And the math behind it looks suspiciously like equations for closed time-like curves. In other words, the quantum system behaved as if information was looping through time. Of course, nobody's building a quantum DeLorean just yet. Quantum effects are tiny, fragile, and incredibly hard to scale up. You can't fit a human inside a probability wave, at least not without a very strong sedative. But these experiments hint at something profound. Maybe time travel, if it exists, won't look like a shiny machine with flashing lights. Maybe it'll look like manipulating the tiniest building blocks of reality. Now, let's step back and appreciate the poetry here. Relativity showed us that time is flexible, bending and stretching under gravity. Quantum mechanics shows us that time might not even be a straight line at all. It might branch, loop, or even dissolve into probabilities. Put the two together and you realize our everyday sense of time, tick-tock, past, present, future, is just a simplified cartoon. The real picture is stranger, richer, and still deeply unfinished. And that's the best part, because every paradox, every experiment, every bizarre quantum effect is an invitation to keep asking questions, to keep dreaming, to keep wondering if one day we'll crack the code and step through time for real. So the next time someone tells you time travel is impossible, just remember, in the quantum world, particles already seem to cheat the rules. And if the building blocks of the universe can bend causality, who's to say we can't one day build Schrödinger's ultimate invention, a quantum time machine? Of course, that machine might also be both working and broken at the same time. But hey, that's quantum physics for you. And speaking of bending time, let's turn now to the math itself. Because behind all these ideas, relativity, wormholes, quantum tricks are equations. Equations that don't just describe the universe but shape it. And some of them are elegant enough to look like poetry. We've been telling stories about wormholes, paradoxes, and even cats that are both alive and dead. But let's pause for a moment. Behind all of it, behind Einstein's bending space-time, Gödel's time loops and quantum shenanigans are equations, numbers and symbols on paper that somehow describe the universe itself. Tonight it's time to peek at the math that actually bends time. Don't worry, you don't need to be a calculus wizard to enjoy this. Think of it less like homework and more like looking at the sheet music behind your favorite song. You don't need to play it yourself to appreciate the beauty. So let's start with Einstein's field equations. These are the heart of general relativity, and they look intimidating. They're often written as G mu null RMD, LG mu null, 8 pi G, say 4, T mu null. Now, if you just had flashbacks to high school math class, relax. This is bedtime storytelling, not an exam. Let's unpack it in plain English. On the left side of the equation is geometry, the curvature of space-time. On the right side is energy and matter, the stuff in the universe. The equation is saying matter tells space-time how to bend, and space-time tells matter how to move. That's it. Think of it like a dance. Matter is the dancer, space-time is the dance floor. If the floor is flat, the dancer moves straight. If the floor is warped, tilted, or curved, the dancer moves differently. The field equations are just the cosmic choreographer, making sure everybody stays in sync. Here's the wild part. Tiny changes in those equations can produce entirely different universes. Plug in one kind of energy, you get a black hole. Plug in another, you get a wormhole. Adjust the terms just right, and you can even get Gödel's rotating universe with closed time loops. It's like having a recipe where swapping out one spice changes the dish from soup to cake. Let's take black holes, for example. The famous Schwarzschild solution is what you get when you solve Einstein's equations for a perfectly spherical, non-rotating mass. That gives you the math for a black hole. Change the assumptions to include rotation, and you get the Kerr solution, which predicts not just black holes but the possibility of time loops inside them. Same equation, different input, completely different reality. This is what makes Einstein's equations so powerful. They don't just describe our universe, they describe all possible universes. They're like a choose-your-own-adventure book for reality, except instead of turn to page 42, it's rotate your space-time cylinder near light speed. And while we're at it, let's talk about the cosmological constant, that little L symbol in the equation. Einstein originally added it to keep the universe static, because he didn't like the idea of it expanding or contracting. Later, when astronomers discovered the universe actually was expanding, Einstein called it his biggest blunder. Except, plot twist. Decades later, scientists discovered that the universe's expansion is accelerating, thanks to something we now call dark energy. And the cosmological constant, turns out it's a pretty good way to describe that. So Einstein's blunder may have been genius in disguise. This is what I love about equations like this. They're not just symbols, they're like treasure maps. You follow them and they lead you to black holes, wormholes, paradoxes, even entire universes you never imagined. Sometimes the equations predict things we don't discover until decades later. The math is ahead of us, waving from the future. But Einstein's equations aren't the only ones that bend time. There's also the Lorentz transformation, which is part of special relativity. These are the equations that tell you how time and space change when you move close to the speed of light. They look a little simpler, and one of the most famous results is this.
Two balls through to a pratch, one brow, the quatretch. See that Porksforth.
Translation: the faster you move v, the slower your clock ticks compared to someone standing still. That's time dilation, right there, in a single formula. Plug in v as your speed, c as the speed of light, and you can calculate how much younger astronauts on fast spaceships will be when they come back home. It's not magic, it's just math. And don't forget thermodynamics. The second law of thermodynamics says that entropy, the measure of disorder, always increases over time. This is where we get the arrow of time. It's why you remember the past but not the future. Why eggs break but don't unbreak. Why your room gets messier by itself but never cleaner. The math of entropy gives time its direction. Without it, time could flow both ways, and you wouldn't know which way was forward. So between relativity, thermodynamics, and quantum mechanics, we have a toolkit of equations that don't just describe time, they shape it. They explain why it stretches, why it flows forward, and how it might, under the right conditions, loop back on itself. But let's not forget, equations aren't the universe. There are maps of it. And like all maps, they can be incomplete. Newton's equations worked beautifully until Einstein came along and showed their limits. Einstein's equations may one day be replaced by something deeper, something that merges relativity and quantum mechanics into a single theory of everything. And when that happens, who knows what new possibilities for time might emerge. Here's the thing though, even if you never solve these equations yourself, there's something deeply comforting about them, because they show us that the universe isn't chaos. It has patterns, it has structure, it has laws. Time may feel slippery when you're waiting in line at the DMV, but underneath there's math keeping it all in place. And the most beautiful part? These equations don't care about us. They don't bend to our wishes, our anxieties, or our sleep schedules. They just are. Eternal, elegant, carved into the fabric of reality itself. Which, let's be honest, is exactly the kind of lullaby a sleepless mathematician should fall asleep to. So next time you see a blackboard covered in incomprehensible squiggles, don't be intimidated. You're looking at the language of time itself. And if those squiggles can bend reality, who's to say they won't one day bend it far enough to let us step into yesterday or tomorrow? But before we get too comfortable with equations, we need to face another stubborn piece of math: entropy. Because as much as relativity loves to bend and twist time, Thermodynamics insists it only flows one way, and that clash between the freedom of relativity and the discipline of entropy is where things get really interesting. By now we've seen time stretch, bend, and even form loops in Einstein's universe. But here's the thing, in your daily life, time feels stubbornly one way. Seconds march forward, eggs break but don't unbreak, coffee cools down, never spontaneously heats back up. Your room gets messier by itself, but it never cleans itself while you sleep, much to the disappointment of parents everywhere. So why is time so one-directional for us when the equations of physics don't actually care? Enter entropy. Entropy is one of those words that sounds fancy but really just means disorder. More precisely, it's a measure of how many different ways the parts of a system can be arranged. A neatly stacked deck of cards has low entropy. A shuffled deck has high entropy. Your tidy desk before finals, low entropy. Your desk after finals, a black hole of entropy. The second law of thermodynamics says entropy always increases in an isolated system. Things go from order to disorder, from simple to messy, from a house of cards standing tall to a sad little pile on the table. And this law is what gives us the arrow of time. Here's the weird part. If you write down Newton's or Einstein's equations, they don't actually care about direction. You can run them forward or backward, and they still make sense. Physics itself doesn't demand that time flows forward, but entropy does. It sets the direction. It's like physics gave time a car, but entropy insisted it only drives east. Let's do a simple example. Imagine you drop a glass on the floor. It shatters, that's normal. Entropy increases. There are more ways for broken shards to be arranged than for one perfect unbroken glass. Now run that movie backward in your head. Shards leap off the floor and form a glass. Possible? In principle, yes. The laws of physics wouldn't forbid it. But the odds are astronomically tiny. It's like winning the lottery 1 trillion times in a row. So in practice, it never happens. This is why time feels one way. It's not because the universe has a law against going backward. It's because the universe is statistically addicted to messiness. Now here's a fun twist. The arrow of time also explains why you can remember the past but not the future. Your brain works by storing information, basically increasing entropy in the process. Memories get laid down as patterns of neurons firing, but those patterns always point to lower entropy states, the past. You don't have memories of the future because the future hasn't yet been fixed into order. It's still open, messy, undetermined. Entropy is why our lives feel like one long walk into the unknown. This raises a fascinating question. If entropy gives us the arrow of time, what was entropy like at the beginning of the universe? The answer, astonishingly low. At the Big Bang, the universe was hot and dense but highly ordered. That low entropy beginning is what gave us room to grow messier over billions of years. Stars formed, galaxies swirled, life crawled out of the oceans, and now you're lying here listening to bedtime math stories, all of it powered by entropy's relentless drive forward. Here's a slightly depressing but oddly cozy thought. Entropy is why you age. Your body is a complicated machine constantly fighting disorder, but the fight isn't fair. Over time, entropy wins. Cells break down, DNA accumulates errors, and you get wrinkles. On the bright side, entropy also gave us stars, sunshine, and pizza, so, trade-offs. Physicists sometimes imagine what would happen in a universe where entropy decreases. A backward world, broken cups reassemble, ashes leap into fireplaces and reform into logs. You wake up younger every morning. Sounds fun, but it would be utterly alien. Cause and effect would feel reversed. You'd remember tomorrow but not yesterday. Honestly, it would make for a confusing sitcom. Now there's still mystery here. Why was the universe's entropy so low at the beginning? Nobody knows. Some say it was just a lucky roll of the cosmic dice. Others think there's a deeper law we haven't discovered yet. Whatever the answer, it's one of the biggest unsolved puzzles in physics. Here's another fun anecdote. When asked why time seems to go forward, the British astrophysicist Arthur Eddington coined the phrase the arrow of time. He admitted the laws of physics don't explain it, but entropy does. His explanation was basically, look, it's obvious to everyone which way time goes, and the reason is entropy. End of story. Not the most satisfying answer, but hey, at least he gave us a cool name. So where does this leave us with time travel? Well, entropy is the universe's way of keeping us honest. You can stretch time, dilate it, maybe even loop it under exotic conditions. But entropy makes sure the overall flow is still forward. You can skip ahead into the future by going fast or hanging near a black hole. But going backward, reversing entropy, is the real challenge. That's why so many scientists think backward time travel might be impossible, unless of course there are loopholes we haven't found yet. And here's a thought to fall asleep to. Even if time travel turns out to be impossible, you're already traveling through time right now. Second by second, entropy nudges you forward, giving your life direction. Without entropy, time wouldn't feel like a journey at all. It would just be a frozen block of existence. Entropy, messy as it is what makes stories possible. So next time you grumble about your messy room, or your burnt toast, or your wrinkled shirt, just remember, all that disorder is the price you pay for having an arrow of time. Without it, life wouldn't have a plot. And with that, let's move on to another mathematical twist. Probability. Because if entropy sets the arrow, probability is what paints the many possible paths. And when it comes to time travel, probability might just be the thing that explains alternate timelines and why every time you hit snooze on your alarm clock, a whole new universe might be born. By now, we've followed time through myths, relativity, wormholes, loops, and entropy's one-way arrow. But let's be honest, what people really love about time travel isn't bending a clock by nanoseconds. It's the big, juicy idea of alternate timelines. The thought that by changing one tiny thing in the past, you could spin reality off in a completely new direction. No grandfather paradoxes, no contradictions, just branching universes as far as the eye can see. And believe it or not, there's math that points to exactly this. Let's start with probability. In everyday life, probability tells you how likely something is. Flip a coin, 50-50. Roll a die, 1 in 6. Eat week-old leftovers, probability of regret, about 100%. We use probability to handle uncertainty. But in quantum mechanics, probability isn't just about ignorance, it's fundamental. Remember Schrödinger's cat. The poor feline in the box is both alive and dead until you open it. That's not because we don't know. It's because in the quantum world, particles really do exist in superpositions of different states. Reality itself is probabilistic. The math that describes this is the wave function. It doesn't say the cat is alive or the cat is dead. It says here's the probability of each. Only when you measure, when you look, does the wave function collapse into one outcome. But here's the catch. Some physicists hated the idea of wave function collapse. They thought, what if both outcomes actually happen? The cat lives and dies, the universe just splits into two, one for each result. That's the many worlds interpretation, proposed by Hugh Everett in the 1950s. In the many worlds view, every quantum event spins off a new branch of reality. Every coin toss, every die roll, every time you choose pizza over salad, boom, new universe. One where you made one choice, one where you made another. Infinite branching forever. The math doesn't collapse, it just multiplies. So what does this mean for time travel? Well, it neatly sidesteps paradoxes. Go back in time, stop your grandfather from meeting your grandmother, and you don't erase yourself. You just hop onto a new branch of the multiverse. In one branch, you still exist. In another, you never did. Both are real, both are valid. And probability math says the universe doesn't mind branching as much as it needs to. It's like a cosmic choose-your-own-adventure book. Did you hit snooze this morning? Somewhere there's a universe where you didn't. Did you buy Bitcoin in 2009? Somewhere you're a billionaire. Did you eat that suspicious gas station sushi? Somewhere you deeply regret it. Every choice, every chance event, every quantum roll of the dice. Each one builds an alternate timeline. Now, this idea might sound like pure science fiction, but it's grounded in the math of quantum mechanics. The wave function doesn't pick a single outcome. It holds them all. Many worlds is one way of taking that math seriously, without adding extra rules. And if it's true, time travel might not mean rewriting history. It might just mean switching tracks to another branch of the multiverse. Here's a funny thought. If there really are infinite timelines, somewhere there's a version of you listening to this exact story, but you're doing it in Spanish, and somewhere else it's you, but you're a giraffe. Probability says if something is possible, some branch of reality contains it, which is both comforting and deeply unsettling. Of course, not everyone loves the many worlds interpretation. Critics say it feels wasteful. Why create infinite universes every time an electron sneezes? That's a lot of cosmic paperwork. Others argue that we don't actually experience these other branches, so maybe they're just math tricks, not real worlds. But whether you buy it or not, the idea has become hugely influential, not just in physics but in pop culture. Movies like Everything Everywhere All at Once and Spider-Man Into the Spider-Verse are basically love letters to the many worlds idea. But let's dig a little deeper into the math of probability itself. In classical statistics, probability is about uncertainty. You roll a die, you don't know what will happen, but one definite result will occur. In quantum mechanics, though, the wave function evolves deterministically. The math says all outcomes evolve. Probability comes in only when you look, when you measure. And many worlds says, no, you don't collapse the wave function, you just follow one branch, while the others continue on without you. This interpretation actually fits neatly with time travel. Imagine stepping into a time machine. You go back, and you change something. From your perspective, history has shifted, but what's really happened is that you've jumped tracks. You're no longer in your original branch, you've moved into a new one. The past you remember still exists, in some other branch. You just don't have access to it anymore. It's like probability applied not just to dice and cats, but to entire histories. The math doesn't forbid it. In fact, it seems to encourage it. Now, here's where things get fun. Some researchers have speculated that quantum computers, machines that harness superpositions and entanglement, might already be exploiting parallel branches of reality. When they run calculations, they try many possibilities at once, then interfere the results to get an answer. In a sense, they're dipping into alternate timelines, borrowing their work and stitching it back together. That's not literally time travel, but it's definitely timeline hopping in miniature. And maybe that's the best metaphor for probability and time travel. Each decision, each quantum event, each roll of the dice is like a fork in the road. We walk one path, but the math whispers that the others are still out there. And if time travel is real, maybe the machine won't take us backward at all. Maybe it will just let us switch roads, slip into one of the countless other timelines running parallel to ours. Of course, probability cuts both ways. In a multiverse of infinite branches, the odds that this branch exists exactly as it is, the odds that you're here now listening to this, are vanishingly tiny. And yet, here you are. Out of all possible histories, you got this one, which, depending on your mood, is either inspiring or just unfair. So next time you flip a coin, remember, somewhere both outcomes happen. Somewhere you win the bet, and somewhere else you don't. And if you ever build a time machine, don't worry too much about paradoxes. Probability math has you covered. You won't erase yourself. You'll just find a new branch of reality waiting for you to step inside. And speaking of people who tried to outsmart time, let's turn to the humans who pushed these ideas the furthest. The mathematicians and physicists who dared to ask, could we actually build a time machine? And if so, what would it take? By this point in our journey, you've seen myths, paradoxes, relativity, wormholes, entropy, and quantum tricks. Time is flexible, moody, and occasionally downright rude. So naturally, some of the smartest humans in history thought, all right, challenge accepted. Let's beat time at its own game. And while none of them have built an actual time machine yet, sorry to disappoint, many of them gave us wild ideas, brilliant math, and a lot of entertaining stories. Let's start with Henri Poincaré. If Einstein was the rock star of relativity, Poincaré was the thoughtful philosopher behind the curtain. He was a French mathematician in the late 1800s, and he was already thinking about the relativity of time before Einstein made it famous. He realized that even something as simple as saying these two clocks strike noon at the same moment isn't so simple. How do you know? Light has to travel between the clocks, and that takes time. Suddenly, simultaneity, whether two events happen at the same time, isn't absolute. It depends on how you measure it. Poincaré saw this before Einstein tied it into a neat theory. And Poincaré wasn't just a dry academic. He had a sense of humor about time too. He once joked that if you lived your life backward, you'd start out old and tired, then get younger and more energetic every day, and finally disappear in a moment of passion. Not bad for a man who spent most of his life with chalk dust on his hands. Next, let's talk about Albert Einstein himself. Yes, we already covered his equations, but what you may not know is that Einstein had a playful side when it came to time travel. He loved paradoxes and would laugh at the idea of using relativity to visit the past, but he also admitted his equations didn't forbid it. In fact, when Gödel showed him that rotating universes could create time loops, Einstein was unsettled but impressed. It was like his math had gotten away from him, running off to play pranks while he was trying to be serious. Then there's Stephen Hawking, the cheeky genius of the 20th century. Hawking thought a lot about time travel, but unlike most physicists, he wasn't afraid to make jokes about it. He came up with the chronology protection conjecture, the idea that the universe prevents time travel paradoxes. But he didn't stop there. In 2009, he threw an actual party for time travelers. Champagne, balloons, hors d'oeuvres, the works. But here's the catch. He didn't send out the invitations until after the party was over. That way only travelers from the future could attend. Nobody showed up. Hawking laughed and called it experimental evidence that time travel doesn't exist. Or maybe the snacks weren't good enough. Another name worth mentioning is Kip Thorne. Thorne was a Nobel Prize-winning physicist who took wormholes seriously enough to write real papers about them. In the 1980s, a student asked him if time machines were possible, and instead of laughing it off, he said, "Let's check the math." That led him to study traversable wormholes, exotic matter, and ways they could in theory act as time machines. Thorne even consulted for the movie Interstellar, making sure the black hole looked scientifically accurate. Thanks to him, millions of people saw a Hollywood version of relativistic time dilation and actually learned something. Thorne's attitude was basically, if the math allows it, let's explore it. We also have Igor Novikov, a Russian physicist who tried to solve the paradox problem by proposing the self-consistency principle. Remember this one? If you travel to the past, you can't change it. Whatever you do was always part of history. Novikov was basically trying to outsmart time by making the rules airtight. No contradictions, no erasing yourself, no grandfather drama. A tidy solution, if a little frustrating for anyone hoping to actually change history. And then there are the dreamers, physicists who thought up wild constructs like the Alcubierre drive. This is the warp drive idea where you compress space-time in front of your spaceship and expand it behind, letting you surf a bubble faster than light without technically breaking the speed limit. It's not exactly time travel, but it messes with space-time in ways that could, under the right conditions, cause time shifts. The only problem, you'd need exotic matter with negative energy, plus more power than exists in the entire galaxy. Small details. But here's what I love about all these mathematicians and physicists. Even though they knew how hard the problem was, even though they admitted it might be impossible, they kept playing with the idea. They treated time like a puzzle, a toy, a cosmic riddle to unravel. And in the process, they gave us insights that shaped science, even outside of time travel. For example, trying to figure out wormholes gave us new ways of thinking about black holes. Wrestling with paradoxes sharpened our ideas about causality and probability. Exploring time dilation helped us invent technologies like GPS. So even if no one ever builds a time machine, the very act of trying to outsmart time has already changed the world. And let's not forget the cultural side. These scientists weren't just influencing each other. They were inspiring writers, filmmakers, and dreamers. Without Einstein, there's no Back to the Future. Without Kip Thorne, no Interstellar. Without Hawking's sense of humor, maybe we'd all take time a little too seriously. So, can we outsmart time? Not yet. Maybe never. But in trying, we discover more about how time actually works. And we keep alive that most human of instincts, curiosity. Because really, what is science if not one long attempt to cheat boredom by asking impossible questions? And maybe that's the real victory. Even if time wins in the end, even if entropy drags us forward and paradoxes shut the doors behind us, we're still clever enough to imagine ways around it. To dream of shortcuts, to write down equations, to laugh about parties for future guests. Outsmarting time may not be possible, but trying is half the fun. Now, speaking of trying, let's take things a step further. What if someone actually wanted to build a time machine? What would the blueprint look like? Spoiler alert, it involves wormholes, cylinders, and more exotic matter than you can shake a stick at. Alright, we've met the dreamers and schemers who tried to outsmart time. Now it's time to roll up our sleeves and actually sketch out a time machine. Don't worry, you don't need to raid Home Depot just yet. We're talking theory here. But still, let's imagine, if you wanted to build a real time machine, what would the blueprint look like? First thing to know, It's not going to be a shiny DeLorean with gull-wing doors. Sorry, Back to the Future fans, real physics demands something much stranger and much bigger. One of the leading candidates is, of course, the wormhole. We already talked about them, tunnels through space-time connecting distant points. The idea is that if you could stabilize one, you could use it as a time machine. Here's how the blueprint works. Step 1. Find or create a wormhole. Step 2. Take one end of it on a high-speed joyride, maybe near light speed. Thanks to time dilation, the traveling end ages slower than the stationary one. Step 3. Bring it back. Now the two ends are out of sync in time. Step 4. Walk in one end, and you come out at the other, arriving in the past or the future relative to where you started. Voila! Instant time machine. Easy, right? Except for one minor detail. Wormholes don't like being open. They collapse instantly. To keep them stable, you'd need exotic matter with negative energy density. And not just a sprinkle, tons of it. Exotic matter is the kind of stuff we've never actually seen in bulk. Some quantum effects hint it might exist, but nobody's exactly found a way to scoop it into buckets. So your blueprint begins with step 1. Discover a new form of matter. Not the most promising start. Another blueprint option is the tippler cylinder. Imagine an infinitely long, incredibly dense cylinder spinning near the speed of light. According to the math, if you orbit this cylinder just right, you can slip into a closed time-like curve and loop back into your own past. Sounds fun. The catch: infinitely long isn't really buildable. Unless you have a hardware store the size of the universe, this blueprint isn't leaving the drawing board. Then there's the idea of using a Kerr black hole. Unlike a simple black hole, a Kerr black hole spins. The math suggests that inside, space-time might allow loops, paths that circle back in time. In theory, you could jump into one and emerge in the past. In practice, you'd have to survive the event horizon, the singularity, the radiation, and the general inconvenience of being spaghettified by tidal forces. Not ideal for tourism. Okay, so wormholes collapse, cylinders are infinite, and black holes are lethal. Is there anything friendlier? Enter the Alcubierre drive. This is a concept dreamed up in the 1990s by Miguel Alcubierre. Instead of moving through space faster than light, you compress space-time in front of your ship and expand it behind, creating a bubble that carries you along. Inside the bubble, you're not breaking the speed limit. Outside the bubble, you look like you're going faster than light. It's basically surfing space-time, and depending on how you manipulate it, you could even create time shifts, meaning your surfboard might also double as a time machine. But again, there's a problem. Exotic matter. The Alcubierre drive needs negative energy, just like wormholes. And not just a little. Calculations once suggested you'd need more energy than exists in the observable universe to move a single spaceship. Later refinements lowered that number, but we're still talking about absurd amounts. The blueprint should probably say, Step 1, convince the cosmos to give you infinite energy. Here's another issue with these blueprints. Even if you built one, you might run into paradoxes. Physicists worry that time machines would create feedback loops of energy, radiation piling up inside until the whole thing collapses. It's like trying to make a karaoke machine that feeds back into itself until it explodes. The math suggests the universe might sabotage your blueprint automatically, keeping causality safe. Hawking's chronology protection strikes again. But let's not be too cynical, because even if these blueprints sound impossible, they've already been useful. Trying to design time machines forced scientists to think about exotic matter, quantum fields, and the structure of space-time in new ways. The questions are so outrageous that they push the boundaries of physics. In other words, time machines are good for science, even if nobody ever builds one. And let's admit it, part of the fun is just imagining, what would a wormhole time machine actually look like? Maybe two giant shimmering portals held open by rings of superconducting magnets, humming ominously. Or maybe it would look boringly practical, like two giant pipes with warning labels. Or maybe, as one physicist joked, it would look like a very good plumber's project. After all, wormholes are basically cosmic plumbing, pipes through space-time. If you can't respect that, what can you respect? So here's the summary of your time machine blueprint options. Wormholes promising but need exotic matter. Tippler cylinders, mathematically fun, physically absurd. Kerr black holes, terrifying death traps. Alcubierre drives cool concept, infinite energy bill. Not exactly build ready. But hey, it's a start. And maybe that's enough, because the real lesson here is that math lets us sketch the impossible. With nothing but equations, we can design machines that bend time, even if the materials don't exist yet. That's the power of mathematics. It lets us build castles or time machines in the air. So the next time you doodle in your notebook, remember, someone once doodled an infinitely long cylinder, and now it's a legitimate solution in general relativity. That's science for you. But before we all get carried away with wormhole blueprints, let's face a sobering possibility. Maybe the universe has built-in safeguards. Maybe time travel is banned by physics itself. And one of the greatest minds of all, Stephen Hawking, thought exactly that. By now, we've drawn up blueprints for wormholes, spinning cylinders, and warp drives. They're bold, imaginative, and let's be honest, wildly impractical. But here's the kicker. Even if you somehow solved all the engineering nightmares, even if you discovered exotic matter in your basement tomorrow, the universe itself might still say, sorry, no time travel allowed. And that's exactly what Stephen Hawking suspected. Hawking was famous for mixing deep insights with cheeky humour. He loved poking holes in wild ideas, and time travel was one of his favourite targets. While he admitted Einstein's equations allowed for closed time-like curves, loops in time, he didn't think nature would ever let them exist in reality. Why? Because paradoxes are messy, and the universe doesn't like mess. He proposed something called the chronology protection conjecture. The idea is that the laws of physics themselves conspire to prevent time machines from forming. In other words, history is safe. No changing the past, no paradoxes, no chaos. So how would the universe enforce this ban? One possibility is that quantum effects pile up in destructive ways whenever you try to make a time machine. For example, if you had a wormhole that could loop back in time, light and particles could enter it and circle endlessly, creating infinite energy buildup. That feedback would destroy the wormhole before you could use it. It's like trying to build a karaoke machine that instantly explodes the first time anyone sings into it. Another argument comes from entropy. Remember the arrow of time. Entropy insists that things go from order to disorder. If you tried to go back and undo entropy, you'd be fighting one of the most fundamental laws of physics. It would be like trying to build a perpetual motion machine. People have tried for centuries, and physics always says no. Time travel might fall into the same forbidden category. And then there's causality itself, the rule that causes come before effects. Causality is the foundation of science. You do an experiment and the result follows. If time loops let causes and effects get scrambled, the whole scientific method falls apart. The universe doesn't seem like the kind of place that would allow its core logic to collapse just so we could have fun buying Bitcoin in 2009. But not everyone agrees with Hawking. Some physicists argue that chronology protection is just a guess, not a proven law. They say, hey, if the math allows it, who are we to say nature forbids it? Maybe paradoxes resolve themselves in ways we don't fully understand yet. Maybe alternate timelines save the day. Maybe causality isn't as sacred as we think. Still, Hawking had a point. The silence of time travelers is suspicious. If backward time travel were easy, wouldn't we have met visitors from the future by now? Unless, of course, they're very good at hiding. Or maybe they showed up, saw what we were doing in the 21st century, and decided not to bother. Honestly, I wouldn't blame them. Here's a fun anecdote. Remember Hawking's time traveler party in 2009? He set up champagne, balloons, snacks, and waited. But he didn't send the invitations until after the party, so only travelers from the future could attend. Nobody came. Hawking called it experimental proof of chronology protection. Of course, maybe the time travelers just had better parties to attend. Or maybe they peeked in, saw the shrimp cocktail and said, hard pass. Another possibility is that time travel is allowed, but only forward. We already know time dilation is real. You can leap into the future by moving fast or hanging out near strong gravity. Maybe that's the only loophole the universe permits. One-way tickets only, no returns. And if you think about it, that makes sense. Forward time travel doesn't create paradoxes. You can't mess up the past if you're only skipping ahead. It's neat, it's tidy, it keeps causality safe. Backward time travel, on the other hand, is chaos waiting to happen. If the universe has a ban list, that's probably at the top. But here's the twist. Even if time travel is banned, we might never know for sure. Physics is full of rules that seemed absolute. until someone found a loophole. For centuries, people thought heavier objects fell faster than lighter ones, until Galileo proved otherwise. Newton thought time was absolute, until Einstein smashed that idea. Maybe one day someone will discover a new law that makes time travel possible after all. Or maybe Hawking was right, and the universe really does have a cosmic bouncer at the door of time, keeping us all in line. No paradoxes, no time tourists, just a one-way trip into the future, courtesy of entropy. And honestly, that's not so bad, because in a way you're already a time traveler. You're moving forward second by second, carried by the universe's flow. You can't stop it, you can't rewind it, but you can marvel at it. And maybe that's the deeper lesson. Time travel might be banned, but time itself is still the greatest mystery ride of all. So where does that leave us? With our imaginations mostly, and with science fiction. Because while physicists argue about equations, storytellers have been happily using time travel for centuries, weaving it into novels, movies, and TV shows. Which brings us to our next chapter, how math and physics have inspired some of the greatest time travel tales in culture, from H.G. Wells to Hollywood. So far, we've looked at the hard math, relativity, wormholes, entropy, quantum cats. But let's be honest, most of us first meet the idea of time travel, not through equations on a chalkboard, but through stories, novels, movies, TV shows. And here's the fun part. Many of those stories were inspired by real math. Sci-fi writers peek at physics, borrow a cool idea, and then spin it into something dramatic, terrifying, or hilarious. Let's start with H.G. Wells. Back in 1895, Wells wrote The Time Machine, and basically invented the genre. Before that, people told stories about magical sleep or divine intervention. But Wells was the first to describe a mechanical device that let you travel through time the way a train travels through space. His machine was a contraption with levers and dials. But the real star was the idea that time was a dimension you could move through. That notion came straight from the mathematical work of the 19th century, where scientists were already toying with the idea of the fourth dimension. Wells just said, "What if you could ride it?" Boom, sci-fi legend. Fast forward a few decades, and along comes Einstein with relativity. Suddenly Wells didn't look so far-fetched. Time really was a dimension, woven together with space. The science caught up with the story, and writers took note. Take Doctor Who, the long-running British series. The Doctor's TARDIS travels through time and space, bigger on the inside, zipping around causality like it's no big deal. While most of it is delightfully silly, and involves more rubber monsters than physics, the core idea that time and space are linked and you can navigate them both is straight out of relativity. The TARDIS is basically a narrative wormhole with mood lighting. Then there's Back to the Future, maybe the most beloved time travel story of all. Doc Brown's DeLorean isn't based on rigorous math. It runs on 1.21 gigawatts of vaguely defined energy, but the movie still plays with real paradoxes. Marty risks erasing himself by interfering with his parents' romance. That's the grandfather paradox in a leather jacket. The trilogy also hints at alternate timelines, with Biff creating a darker reality by tampering with history. That's basically the many worlds interpretation in popcorn form. Hollywood loves relativity too. Christopher Nolan's Interstellar made headlines for its scientifically accurate black hole, thanks to Kip Thorne's consulting. In the movie, time dilation near a massive black hole means that while hours pass for the astronauts, decades pass back on Earth. That's not artistic exaggeration, that's literally how relativity works. The math says gravity slows time, and Nolan used that to break hearts on screen. If you cried during the scene where the astronaut's daughter grows old without him, you can thank Einstein's equations. And let's not forget Avengers Endgame. The movie famously threw shade at Back to the Future, saying, "Time travel doesn't work like that." Instead, the Avengers used a version of the many worlds idea. Travel into the past, change something, and you don't rewrite your timeline. You create a new branch. That's exactly what quantum physicists like Everett proposed. Sure, the movie also involved Ant-Man in a taco scene, but the underlying theory wasn't nonsense. Even video games get in on the fun. The Legend of Zelda: Ocarina of Time has Link moving back and forth between childhood and adulthood, essentially treating time as a landscape. BioShock Infinite dives into branching timelines and alternate realities inspired by quantum mechanics. Game designers love time travel because it's the ultimate cheat code for narrative design. If something doesn't make sense, just say it's a paradox and keep playing. But it's not just that sci-fi borrows from math. Sometimes math borrows back. Ideas that first appeared in fiction end up inspiring physicists. For example, wormholes as portals were popularized by sci-fi long before serious physicists explored them in papers. Kip Thorne admitted that student questions about Star Trek were part of what pushed him to study traversable wormholes seriously. In a strange way, fiction dared math to catch up. And honestly, that's the magic of it. Science and sci-fi are in constant dialogue. Math whispers, here's a weird equation that says space-time could fold. Writers shout, cool, let's build a time machine shaped like a phone booth. Then kids grow up watching those stories, get curious, become scientists, and push the math further. It's a feedback loop of imagination. Here's a fun anecdote. Carl Sagan, the famous astronomer, once wanted to use a black hole for time travel in his novel Contact. But he wasn't sure if the physics checked out, so he called Kip Thorne, who said, nah, black holes are too messy, but wormholes, those could work. Thorne then wrote actual papers on wormholes, partly because a novelist asked him to. That's right, a sci-fi story literally triggered serious research. So the next time someone says sci-fi is just fantasy, remember, sometimes the fantasy writes the homework assignment for physics, and physics, being a diligent student, hands in the answer years later. Of course, not all sci-fi gets the math right. Plenty of stories just wave their hands and say quantum or flux capacitor and move on. And that's okay, because the point of these stories isn't to be accurate, it's to capture our imagination, and math at its best does the same thing. So here's the takeaway. From H.G. Wells' Brass and Gear Machine to Hollywood's CGI wormholes, sci-fi time travel is rooted in real mathematics, relativity, paradoxes, entropy, probability. They've all made their way from blackboards to blockbusters, and in return the stories keep people dreaming, keep the questions alive, and keep inspiring the next generation of sleepless mathematicians. Which brings us to a bigger, more personal question. What if we could really do it? What if all the math, all the equations, all the wormholes and paradoxes weren't just stories but blueprints? What would time travel mean for us, for history, for free will, for the way we see ourselves? What if we could really do it? We've played with paradoxes, bent time with equations, surfed wormholes, and even peeked at Hollywood's favourite versions of the math. But now let's ask the question that's been hovering in the background the whole time. What if we could really do it? What if time travel weren't just equations and stories, but a real possibility? First, let's think about the personal side. If someone gave you a working time machine tomorrow, what would you do? A lot of people say they'd go back and fix mistakes, buy Bitcoin early, study harder for that math test, or maybe avoid that haircut from the 2000s. But here's the tricky bit. If the past can actually be changed, then every little action ripples outward. Save one person in the past and who knows how the future shifts. The butterfly effect isn't just a cliché. Tiny changes can explode into huge consequences. Accidentally sneeze in the wrong century, and you might come back to a world ruled by hyper-intelligent ducks. But maybe paradoxes don't allow that. Maybe, as Novikov suggested, history is self-consistent. In that case, you couldn't change the past, you could only fulfill it. Travel back to fix your mistake, and you'd realize your actions were always part of the timeline. The math says, sorry, no takebacks. It's history with auto-lock. So if the past is messy, what about the future? Traveling forward is easier. Time dilation already proves it's possible. But imagine what that means socially. You could jump centuries ahead, skipping over wars, pandemics, and awkward family gatherings. But you'd also lose everything in between. Everyone you know would be gone. Civilization might not even look recognizable. You'd be a tourist in your own species' story, forever disconnected. Time travel forward sounds exciting until you realize it's also a form of exile. And then there's the collective question. What would happen if humanity, as a whole, had time travel? Think about it. Historians would go wild. Every mystery who built Stonehenge, what really happened to Amelia Earhart, whether Shakespeare actually wrote his plays, solved overnight. Museums would have first-hand footage instead of dusty artifacts. Sounds amazing, right? But now think about politicians. Imagine every election being refought, every war being rewaged, every law being tampered with. History wouldn't just be messy, it would be chaos. Every side would be rewriting the past to suit themselves. You think Twitter arguments are bad? Try living in a world where reality itself changes every few hours. Economics would get weird too. Insider trading? Forget it. Just peek at tomorrow's stock market. Lotteries? Pointless, unless the rules change to time travelers not eligible. Honestly, you'd probably see whole governments banning or policing time travel the way we regulate nuclear weapons, because the ability to rewrite history would be the ultimate power. Then there's the philosophical side. If we can move through time freely, does free will even exist? Are we just passengers on a fixed loop, or do we carve new timelines with every choice? The block universe idea says past, present, and future are all equally real, like pages in a book. You can flip around, but the story is already written. That would mean free will is an illusion. Every decision you make was always going to be made. On the other hand, if many worlds is true, then every choice spins off new realities. Free will exists, but at the cost of infinite universes branching like a cosmic tree. Either way, time travel forces us to confront what it even means to be human. Are we authors of our story, or just characters in a script? Here's another angle. Morality. If you had the power to change the past, would you be obligated to? If you could stop a war, prevent a tragedy, or save millions of lives, is it wrong not to? Or is it dangerous to even try, since you might create worse outcomes? Suddenly, time travel isn't just a toy, it's a moral burden. Every action carries infinite responsibility. And of course, there's the existential question. Maybe we already do have time travelers among us. Maybe they blend in, careful not to disrupt causality. Maybe that friend who always seems to know what's going to happen next is secretly on their third playthrough of history. Hawking's empty party aside, it's impossible to prove we don't have visitors, which means for all we know, someone could be editing reality right now. Comforting thought, isn't it? But let's end on a gentler note, because as wild as these questions are, there's something kind of beautiful in them. Even if time travel never becomes real, the very act of imagining it makes us see our own lives differently. Every choice you make, every chance you take, is a branch in your personal timeline. You don't need a time machine to look back on your past or wonder about your future. You do that every day. Memory and imagination are the time machines we already carry in our heads. So what if we could really do it? Maybe it would break the world. Maybe it would save it. Or maybe the universe has wisely locked that door, leaving us only with dreams. But dreaming is enough, because sometimes the what if is more powerful than the what is. And in the end, the math of time travel isn't just about bending equations, it's about stretching our imagination. And now, as we approach the end of our sleepless journey, it's time to wind down. We've bent time, wrestled paradoxes, and peeked at infinite universes. Let's close with one last chapter, a calm reflection on the mystery of time itself, and why, even if we never master it, it will always fascinate us. And here we are. After 2 hours of wandering through paradoxes, wormholes, quantum cats, and philosophical headaches, we've arrived at the quiet end of our journey. Time travel may still be just an idea, but the ride has been worth it. Because even if we never build a time machine, the act of thinking about time, what it is, how it bends, how it flows, teaches us something about ourselves. So let's take a breath. Think about what we've covered. We started with myths, ancient stories about warriors sleeping for centuries, or gods who could slip outside of time. Then we moved into the age of mathematics, with Newton's ticking clock universe and Einstein's grand revelation that time isn't absolute at all. We dipped into Gödel's strange loops, Hawking's playful skepticism, and the dizzying world of quantum mechanics, where probability itself seems to stretch reality. Along the way, we laughed about paradoxical grandfathers, imagined infinite universes, and even threw a time traveler's party that nobody showed up to. What does all of this mean? Maybe nothing more than this. Time is bigger than us. It's stranger than us. And yet, we are woven into it. Here's the paradox of being human. We can't step outside of time, but we can imagine it. We can picture universes where time runs backward, where every choice splits reality in two, where wormholes connect to distant galaxies like subway stops. That act of imagination is its own kind of time travel. Every story, every equation, every dream of the future or memory of the past, that's us stepping beyond the present, if only in thought. And there's something comforting in that, because no matter how confusing the math gets, or how frustrating the paradoxes are, time itself keeps flowing. You don't have to solve Einstein's equations to live in space-time. You don't need exotic matter to experience the arrow of entropy. You're already traveling 1 second per second, always forward, the simplest journey, the only guaranteed one. So maybe the real lesson isn't how to build a time machine, but how to appreciate the time we already have. Think about it. Every moment is unique, unrepeatable. Once it's gone, it never comes back. And that's not a flaw. That's what gives life its flavor. If time could be reversed, maybe we'd never value the present. If we could jump back endlessly, maybe we'd never truly live forward. Of course, that doesn't mean we shouldn't dream. Dreaming of time travel lets us stretch the limits of what's possible. It inspires science, art, philosophy, and the occasional Hollywood blockbuster. And even if those dreams never leave the page, they make the universe feel a little bigger, a little more mysterious, a little more alive. So tonight, as you lie here listening, think of yourself as a traveller, not in a DeLorean, not through a wormhole, but in the simplest way, riding the river of time. Every breath you take is another step forward. Every heartbeat is a tiny tick of the cosmic clock. And if you drift off to sleep, don't worry, you're still travelling. You'll close your eyes in one moment and wake up in another, your own little leap through time. And maybe that's all the time machine we really need. Because here's the quiet truth. The future will come, whether we rush toward it or not. The past will stay, whether we try to rewrite it or not. And the present, this moment right now, is where we live. That's where all the math, all the history, all the imagination comes together. So let's let the paradoxes rest for now. Let's set aside the wormholes and the equations. Time doesn't need us to solve it tonight. It only asks us to feel it, to notice the gentle flow, the seconds slipping by, the way the universe carries us along. And if you find yourself drifting off, that's okay. That's just time doing its work, pulling you forward into tomorrow. When you wake, you'll have travelled, not across centuries or galaxies, but across the simple, ordinary miracle of a night's sleep. And who knows, maybe in your dreams you'll build a time machine anyway. Maybe you'll meet Gödel or Einstein, or ride a wormhole to the edge of the universe, or sit with Schrödinger's cat while it debates its existence. Dreams are their own kind of time travel after all. So let's end here, not with answers, but with a quiet appreciation of the mystery. Time is vast, strange, and unsolved, and yet it is also gentle, constant, and close. It's in your breath, your heartbeat, your dreams. Thank you for travelling with me tonight. Sleepless mathematician to sleepless listener. May your journey forward be full of wonder, curiosity, and maybe just a little humour. And now, it's time to rest. Because even the best time travellers need sleep.